Imagine looking out into the night sky and seeing countless stars arranged in vast, swirling patterns of light, as though the universe itself had created its own masterpieces. These intricate, awe-inspiring formations are spiral galaxies, and they have captivated humanity for centuries. But how do these grand structures come to exist? Why do they take on such mesmerizing shapes, and how do they evolve over billions of years? These questions have puzzled astronomers and sparked debates for decades, leading to some of the most fascinating discoveries in astrophysics. To understand spiral galaxies, you first have to realize they are not just random collections of stars. They are cosmic cities, home to billions or even trillions of stars, gas, dust, and dark matter. They are held together by gravity and shaped by complex processes that span timescales so vast they're almost impossible to comprehend. These galaxies are more than just beautiful. They're a window into the past, a glimpse of how the universe itself grows and changes. One of the most striking features of spiral galaxies is their shape. They have sprawling arms that radiate outward like the spokes of a wheel, often dotted with clusters of young blue stars. At the center lies a dense, glowing bulge, home to older stars and often a supermassive black hole. Surrounding this is a halo of faint stars and dark matter that extends far beyond what we can see. Together, these components form a structure that is both dynamic and incredibly stable, a delicate balance of motion and gravity that has persisted for billions of years. But how does such a structure form? The story of spiral galaxies begins in the chaotic aftermath of the Big Bang, around 13.8 billion years ago. In those early moments, the universe was a hot, dense soup of particles. As it expanded and cooled, matter began to clump together under the influence of gravity, forming the first stars and small galaxies. Over time, these smaller structures collided and merged, creating larger galaxies. Some of these grew into elliptical shapes, while others flattened into disks, eventually forming the spirals we see today. The formation of spiral arms is one of the most intriguing mysteries of these galaxies. For years, scientists wondered why the arms don't simply dissipate over time. After all, galaxies rotate, and their stars and gas move at different speeds depending on how far they are from the center. If the arms were made of the same stars and gas all the time, they would eventually smear out like the colors of a spinning top. So, what keeps them intact? The answer lies in a concept known as density waves. These are like traffic jams in space, a region of higher density that moves through the galaxy's disk. As stars and gas move through this wave, they slow down and clump together, creating the bright, star-filled arms. Once they pass through the wave, they move on, but the wave itself remains, continually triggering the birth of new stars. This process explains why spiral arms appear so prominent, and why they seem to shine with young, hot stars. The central bulge of a spiral galaxy is another fascinating feature. It's typically made up of older, redder stars that formed earlier in the galaxy's history. Many bulges also harbor supermassive black holes, which can have masses millions or even billions of times that of the Sun. These black holes play a crucial role in regulating the growth of their galaxies. When they consume matter, they release enormous amounts of energy, which can heat up surrounding gas and prevent it from forming new stars. This feedback mechanism helps explain why some galaxies stop forming stars altogether and become quenched. Surrounding the visible parts of spiral galaxies is a mysterious halo of dark matter. This invisible substance doesn't emit or absorb light, so we can't see it directly. However, its presence is inferred from the way it affects the motion of stars and gas. Without dark matter, spiral galaxies would fly apart, as their visible mass isn't enough to hold them together. Understanding dark matter remains one of the biggest challenges in modern astrophysics, and spiral galaxies are key to unraveling this cosmic puzzle. The evolution of spiral galaxies is a story of constant change. While they may look serene and unchanging from our perspective, they are actually dynamic and ever-evolving. They grow by merging with smaller galaxies, a process that can also trigger bursts of star formation. However, not all mergers are peaceful. When two galaxies of similar size collide, the resulting chaos can disrupt their structures, often transforming them into elliptical galaxies. Despite this, many spirals manage to retain their shape for billions of years, a testament to the delicate balance of forces at play. Another factor influencing the evolution of spiral galaxies is their environment. Galaxies located in dense clusters, surrounded by many neighbors, are more likely to interact with others. These interactions can strip away gas, distort their shapes, or even trigger the formation of new stars. In contrast, galaxies in more isolated regions tend to evolve more quietly, gradually consuming their gas and forming stars at a steady rate. One of the most exciting areas of research in spiral galaxies is the study of their star formation. Stars are born in dense clouds of gas and dust, often located in the spiral arms. These regions, known as star-forming regions, are like cosmic nurseries, where gravity pulls gas together until it becomes dense enough to ignite nuclear fusion. The process of star formation is not only beautiful but also crucial for understanding the life cycle of galaxies. As we study spiral galaxies, we also learn more about our own galaxy, the Milky Way. It is a barred spiral galaxy, meaning it has a bar-like structure of stars running through its center. The Milky Way's spiral arms are home to countless stars, including our Sun, which orbits the galactic center at a distance of about 27,000 light-years. By studying other spiral galaxies, we gain insights into the history and future of our cosmic home. The study of spiral galaxies is far from complete. With advances in technology, such as the Hubble Space Telescope and the upcoming James Webb Space Telescope, astronomers are uncovering new details about these magnificent structures. From the role of dark matter to the effects of black holes, every discovery brings us closer to understanding the intricate dance of forces that shapes the universe. The mysteries of spiral galaxies extend far beyond what we can observe with our current technology. As we delve deeper into their complexities, new questions arise, fueling our curiosity about the processes that govern their formation, structure, and evolution. One particularly fascinating aspect is the relationship between spiral galaxies and their interstellar medium, the gas and dust that fills the space between stars. This medium plays a crucial role in star formation, yet its behavior and distribution are anything but uniform. Spiral galaxies often exhibit striking patterns of gas density, with the densest regions concentrated in their spiral arms. These regions are where stars are born, as gravity compresses the gas into dense clumps that eventually ignite nuclear fusion. But why does the gas settle in these specific areas? The answer lies in the density wave theory mentioned earlier. As the density wave moves through the galaxy, it compresses the gas it encounters, creating ideal conditions for star formation. This process is not instantaneous. It can take millions of years for a gas cloud to collapse into a star. Yet, when viewed on cosmic timescales, the spiral arms of a galaxy appear to be bustling factories of star production. Interestingly, not all spiral galaxies are equally active in forming stars. Some, known as grand design spirals, have well-defined arms where star formation is vigorous and organized. Others, called flocculent spirals, have patchy, less defined arms and lower rates of star formation. The reasons for these differences are not fully understood, but they likely involve a combination of factors, including the galaxy's mass, composition, and environment. For example, galaxies with more abundant gas reserves are generally more active in producing stars, while those in denser galactic clusters may have their gas stripped away, reducing their star-forming potential. Another intriguing feature of spiral galaxies is the way they rotate. Unlike a solid object, where every part rotates at the same speed, galaxies exhibit differential rotation. This means that stars and gas closer to the center complete their orbits faster than those farther out. This rotational behavior is a critical clue in understanding the distribution of mass within galaxies, as it reveals the influence of dark matter. Observations show that the outer regions of spiral galaxies rotate much faster than expected based on their visible mass alone. This discrepancy points to the presence of a vast halo of dark matter that envelopes the galaxy, providing the additional gravitational pull needed to explain the observed rotation rates. The interplay between dark matter and spiral galaxy structure is an area of intense research. Dark matter not only helps stabilize the galaxy's rotation but may also influence the formation of spiral arms. Simulations suggest that the gravitational effects of dark matter can amplify density waves, making the arms more pronounced and long-lasting. However, the exact nature of dark matter remains one of the greatest unsolved mysteries in physics, and understanding its role in galaxy dynamics is a key goal for astronomers. The central bulges of spiral galaxies add another layer of complexity to their study. These bulges, often spherical or elongated, are densely packed with older stars and serve as the galaxy's core. In many cases, the bulge harbors a supermassive black hole, a monstrous object with a mass millions or billions of times that of the Sun. These black holes are not just passive observers, they actively shape their surroundings. When material falls into a supermassive black hole, it releases enormous amounts of energy in the form of radiation and powerful jets. This energy can heat the surrounding gas, preventing it from cooling and collapsing to form new stars. This feedback mechanism is thought to play a critical role in regulating galaxy growth and evolution. Supermassive black holes also provide clues about a galaxy's history. Observations reveal a strong correlation between the mass of a galaxy's central black hole and the properties of its bulge, such as its mass and velocity dispersion. This relationship, known as the black hole bulge connection, suggests that the growth of a black hole and its host galaxy are closely linked. How this connection develops is still an open question, but it likely involves a combination of gravitational interactions, mergers, and feedback processes. Mergers, in particular, are a dramatic chapter in the life of spiral galaxies. When two galaxies collide, the resulting gravitational chaos can dramatically alter their structures. In some cases, mergers can transform spiral galaxies into elliptical ones, as their disks are disrupted and their stars are scattered into more random orbits. However, not all mergers lead to such drastic changes. Minor mergers, where a spiral galaxy absorbs a much smaller galaxy, can trigger bursts of star formation without destroying the galaxy's overall structure. These events contribute to the growth of spiral galaxies over time, adding new stars and enriching their gas with heavy elements. The role of environment in shaping spiral galaxies cannot be overstated. Galaxies in isolated regions, known as the field, have relatively peaceful lives, evolving slowly over billions of years. In contrast, galaxies in dense clusters experience frequent interactions with their neighbors. These interactions can strip away gas through a process called ram pressure stripping, where a galaxy moving through a cluster's hot, diffuse gas loses its own gas. Such events can quench star formation, turning a once vibrant spiral into a more passive galaxy. Despite the challenges posed by these environmental factors, spiral galaxies are remarkably resilient. Their ability to maintain their structure over billions of years is a testament to the delicate balance of forces at play. Gravity, rotation, star formation, and feedback processes all work together to create and sustain these magnificent structures. The ongoing study of spiral galaxies not only enhances our understanding of the universe but also deepens our appreciation for the intricate beauty of cosmic evolution. As we continue to explore the mysteries of spiral galaxies, the advent of new technologies promises to revolutionize our understanding. Instruments like the James Webb Space Telescope and the Vera C. Rubin Observatory will provide unprecedented views of these galaxies, revealing details that were previously hidden. From the earliest stages of their formation to the complex interplay of forces that shape their evolution, these tools will help unlock the secrets of spiral galaxies, bringing us closer to answering the profound questions that have fascinated humanity for generations. The future of studying spiral galaxies lies in the incredible advancements in technology and observational methods, which are unlocking mysteries we could only dream of solving in the past. Among the most exciting tools are space-based telescopes, such as the James Webb Space Telescope, JWST, which has already begun revolutionizing our understanding of the universe. Its ability to observe in infrared wavelengths allows astronomers to peer through clouds of gas and dust, revealing the hidden structures of spiral galaxies and the processes occurring deep within their arms and bulges. One of the primary focuses of current research is understanding the earliest stages of spiral galaxy formation. Observations of distant, ancient galaxies, those formed when the universe was only a few billion years old, reveal structures that could be the precursors to the magnificent spirals we see today. These proto-galaxies often lack the well-defined arms and central bulges of mature spirals, instead appearing as irregular, chaotic assemblies of stars, gas, and dark matter. By studying these early formations, scientists aim to piece together the evolutionary steps that lead to the distinct, organized structures of modern spiral galaxies. Computer simulations play a crucial role in this endeavor. By creating models of galaxy formation and evolution, researchers can test hypotheses about the factors that influence spiral galaxy development. These simulations incorporate complex physics, including the effects of gravity, gas dynamics, star formation, and feedback from supernovae and black holes. By comparing the results of these simulations with actual observations, scientists can refine their models and gain deeper insights into the processes that shape spiral galaxies over billions of years. One area of active investigation is the role of angular momentum in the formation of spiral galaxies. Angular momentum refers to the rotational motion of a system, and it is a fundamental property that influences the structure of galaxies. During the early stages of galaxy formation, gas clouds acquire angular momentum through interactions with other matter. This rotation causes the gas to flatten into a disk, setting the stage for the development of spiral arms. The specific distribution of angular momentum can determine the size and shape of a galaxy, as well as the prominence of its spiral features. The influence of dark matter on angular momentum and galaxy structure is another key topic of research. Dark matter, which makes up about 85% of the total matter in the universe, interacts with ordinary matter through gravity. Its presence is essential for the formation of large-scale structures in the cosmos, including galaxies. Observations and simulations suggest that dark matter halos play a significant role in stabilizing the disks of spiral galaxies, allowing them to maintain their shape over time. However, the exact nature of dark matter and its interactions with baryonic, normal, matter remains some of the biggest unanswered questions in astrophysics. Spiral galaxies also offer a unique laboratory for studying the life cycle of stars and the chemical enrichment of the universe. As stars form and evolve, they produce heavy elements through nuclear fusion, which are then released into the surrounding medium when the stars die. These elements are incorporated into subsequent generations of stars, gradually increasing the metallicity, heavy element content, of the galaxy. By analyzing the distribution of elements across a spiral galaxy, astronomers can reconstruct its star formation history and gain insights into the processes that drive chemical evolution. Another fascinating aspect of spiral galaxies is the behavior of their magnetic fields. Although invisible to the naked eye, magnetic fields are a fundamental component of galaxies, influencing the motion of charged particles and the dynamics of gas and dust. Observations using radio telescopes have revealed intricate magnetic field patterns in spiral galaxies, often aligned with their arms. These fields may play a role in shaping the structure of the interstellar medium and guiding the flow of cosmic rays. Understanding how these fields are generated and maintained is an ongoing challenge, requiring a combination of observational and theoretical approaches. As we probe deeper into the mysteries of spiral galaxies, one question looms large: how do they fit into the broader context of cosmic evolution? The distribution and properties of spiral galaxies provide valuable clues about the large-scale structure of the universe and the processes that govern its growth. For instance, the prevalence of spiral galaxies in certain environments, such as galaxy groups and clusters, can reveal information about the gravitational interactions and mergers that shape the cosmos. By studying these patterns, astronomers hope to uncover the underlying principles that govern the formation and evolution of galaxies on all scales. Moreover, spiral galaxies are not just static structures. They are dynamic, ever-changing systems. The interplay between stars, gas, dark matter, and other components creates a constantly shifting balance of forces. For example, interactions with neighboring galaxies can induce tidal forces that distort the spiral arms or trigger bursts of star formation. Over time, these interactions can even transform a spiral galaxy into a completely different type, such as an elliptical or lenticular galaxy. Observing these processes in action provides a glimpse into the complex web of interactions that shape the universe. The study of spiral galaxies also has profound implications for understanding our own Milky Way. As a barred spiral galaxy, the Milky Way shares many characteristics with other spirals, making it an ideal case study for exploring broader questions about galaxy formation and evolution. Detailed surveys of the Milky Way's structure, composition, and motion offer invaluable data for testing theories and refining models. Moreover, the discovery of exoplanets within the Milky Way adds another layer of complexity, as researchers explore how the galaxy's properties influence the formation and habitability of planetary systems. Looking to the future, the next generation of telescopes and observatories promises to revolutionize our understanding of spiral galaxies. Projects like the Square Kilometre Array, SK, and the European Extremely Large Telescope, ELT, will provide unprecedented resolution and sensitivity, enabling astronomers to study galaxies in greater detail than ever before. These instruments will allow us to observe the faintest and most distant spiral galaxies, shedding light on their origins and evolution across cosmic time. As we stand on the cusp of these discoveries, the study of spiral galaxies serves as a reminder of the profound interconnectedness of the universe. From the intricate patterns of their spiral arms to the vast halos of dark matter that surround them, these galaxies encapsulate the beauty and complexity of the cosmos. Each new insight into their mysteries brings us one step closer to understanding the fundamental processes that govern the universe and our place within it. The evolution of spiral galaxies is also intricately tied to the interplay between their internal components and external influences. To unravel the complexities of these systems, astronomers have dedicated significant attention to understanding the role of feedback processes, which include the influence of stellar winds, supernova explosions, and active galactic nuclei, AGN. These feedback mechanisms regulate star formation by heating, compressing, or expelling gas, ultimately affecting the growth and structure of the galaxy. One particularly fascinating phenomenon is the effect of supermassive black holes at the centers of many spiral galaxies. While spiral galaxies are not typically dominated by AGN activity like their elliptical or irregular counterparts, their central black holes still play a significant role in shaping the surrounding environment. The energy released by material falling into these black holes can create powerful jets or outflows that influence the galaxy's interstellar medium. These processes, while occurring on relatively small scales, have far-reaching implications for the overall evolution of the galaxy. The role of spiral arms in star formation is another critical area of study. These arms are not merely decorative features but are sites of intense star-forming activity. The density wave theory provides a framework for understanding how spiral arms act as traffic jams in the galaxy's disk, compressing gas and triggering the collapse of molecular clouds into new stars. This process is not uniform, however, as the properties of the gas, the speed of the spiral pattern, and the gravitational influence of nearby structures all contribute to variations in star formation rates across the galaxy. Interestingly, not all spiral arms are created equal. Some galaxies exhibit tightly wound, symmetrical arms, while others display looser, more fragmented patterns. The reasons behind these differences are still an active area of research. Factors such as the mass and distribution of the galaxy's dark matter halo, the presence of a bar structure in the central region, and past interactions with other galaxies all play a role in determining the appearance and behavior of spiral arms. Observing and modeling these variations can help scientists identify the underlying principles that govern the formation of spiral structures. Beyond the arms themselves, the central bulges of spiral galaxies offer another layer of complexity. These dense, spheroidal regions contain some of the oldest stars in the galaxy, providing a window into its early history. The formation of bulges is a topic of ongoing debate, with competing theories suggesting that they may form through the coalescence of smaller protogalaxies, the secular evolution of the disk, or a combination of both processes. Understanding the origins of bulges is essential for piecing together the full evolutionary history of spiral galaxies. Meanwhile, the outer regions of spiral galaxies present their own set of challenges and mysteries. These areas, often dominated by faint, diffuse structures, provide clues about the galaxy's interactions with its surroundings. For example, tidal streams and stellar halos can reveal evidence of past mergers with smaller galaxies, as well as the influence of nearby companions. These interactions not only shape the visible structure of the galaxy but also contribute to its growth by adding new material to the disk and halo. The discovery of ultra-diffuse galaxies, UDGs, has added a new dimension to our understanding of spiral galaxy evolution. These faint, low-surface brightness galaxies often appear to lack the dense cores or prominent arms of typical spirals, yet they may still share similar formation histories. Studying UDGs can provide valuable insights into the conditions under which spiral galaxies form and the factors that lead to their diversity in structure and appearance. As we continue to explore the evolution of spiral galaxies, one of the most intriguing questions is how their properties are influenced by the large-scale structure of the universe. Spiral galaxies are not isolated entities. They exist within a cosmic web of filaments, voids, and clusters. Their formation and evolution are shaped by their interactions with this larger structure, as well as by the processes that govern the distribution of matter on cosmic scales. For example, the density of the local environment can affect the rate of galaxy mergers, the availability of gas for star formation, and the prevalence of tidal interactions, all of which influence the characteristics of spiral galaxies. Recent advances in observational technology have opened new windows into the study of these interactions. Instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Very Large Telescope, VLT, have provided unprecedented views of the cold gas and dust that fuels star formation in spiral galaxies. By analyzing the distribution and motion of these components, astronomers can gain a deeper understanding of the processes that drive galaxy growth and evolution. The role of cosmic time in shaping spiral galaxies is another area of intense investigation. Over billions of years, galaxies undergo significant changes in structure, composition, and activity. Observations of distant galaxies, those that existed in the early universe, offer a glimpse into the past, allowing astronomers to reconstruct the evolutionary pathways that lead to the present-day population of spirals. These studies also reveal how the properties of galaxies are influenced by the changing conditions of the universe, such as the decline in star formation rates and the depletion of available gas over time. The quest to understand spiral galaxies is far from over. Each new discovery raises new questions, challenging our assumptions and expanding our horizons. As we look to the future, the development of even more advanced technologies promises to revolutionize our understanding of these cosmic marvels. From uncovering the secrets of their formation to unraveling the complexities of their evolution, the study of spiral galaxies remains one of the most exciting frontiers in astrophysics, offering endless opportunities for exploration and discovery. The dynamics of spiral galaxies extend far beyond their visible components. While their iconic arms and bulges dominate images captured by telescopes, much of the story of their evolution lies in the unseen forces and materials that shape their development. One of the most significant of these is dark matter, an enigmatic substance that accounts for a vast majority of the mass in the universe. Although dark matter does not emit, absorb, or reflect light, its gravitational influence is unmistakable in the behavior of spiral galaxies. The rotation curves of spiral galaxies provide compelling evidence for the presence of dark matter. Observations show that the outer regions of these galaxies rotate at nearly constant speeds, rather than slowing down as one might expect if only visible matter were present. This discrepancy suggests that an unseen halo of dark matter extends far beyond the visible disk, exerting the gravitational pull necessary to maintain these high rotational velocities. Understanding the distribution and properties of dark matter is critical to unraveling the full story of spiral galaxy evolution. But the influence of dark matter is not limited to the internal dynamics of individual galaxies. It also plays a crucial role in their interactions with the larger cosmic environment. Spiral galaxies often reside in groups or clusters, where gravitational interactions with other galaxies and the surrounding dark matter halos shape their structure and behavior. These interactions can lead to dramatic events, such as mergers, tidal stripping, and the accretion of gas and stars from nearby systems. One particularly intriguing aspect of these interactions is the phenomenon of galactic cannibalism, in which a larger spiral galaxy consumes smaller companions. As these smaller galaxies are pulled in by the gravitational force of the larger system, their material becomes integrated into the larger galaxy's disk and halo. This process not only contributes to the growth of the spiral galaxy but also leaves behind telltale signatures, such as streams of stars and gas that arc across the sky. Studying these remnants provides valuable clues about the history of galaxy interactions. The concept of mergers and interactions becomes even more fascinating when considering the role of major mergers, where two galaxies of comparable size collide and eventually merge into a single system. While such events are more commonly associated with the formation of elliptical galaxies, they can also play a role in the evolution of spirals. In some cases, a major merger can trigger the formation of new spiral structures or even lead to the creation of a barred spiral galaxy. However, the outcome depends on a delicate balance of factors, including the relative sizes of the merging galaxies, the speed and angle of the collision, and the presence of gas in the system. Beyond the realm of visible matter and dark matter, the role of magnetic fields in shaping spiral galaxies has also garnered significant attention. Although less well understood than gravitational forces, magnetic fields influence the behavior of charged particles within the galaxy, affecting processes such as gas dynamics and star formation. Observations using radio telescopes have revealed intricate magnetic field patterns in spiral galaxies, often aligned with their arms. These fields may play a role in maintaining the stability of the spiral structure and regulating the flow of gas into star-forming regions. Another frontier in the study of spiral galaxies lies in their chemical composition. The distribution of elements within a galaxy provides a record of its star formation history and the processes that have enriched its interstellar medium. Heavier elements, known as metals, in astronomical terms, are produced in the cores of stars and dispersed into the galaxy through supernova explosions. By mapping the metallicity of stars and gas across a spiral galaxy, scientists can trace the patterns of star formation and the movement of material over time. Interestingly, the chemical composition of spiral galaxies is not uniform. The central regions, including the bulge and inner disk, tend to have higher metallicities than the outer regions. This gradient reflects the fact that star formation has been more intense and sustained in the inner parts of the galaxy, leading to a greater accumulation of heavy elements. However, interactions with other galaxies, as well as internal processes such as the migration of stars and gas, can disrupt these gradients and create more complex patterns. In recent years, the discovery of dwarf galaxies orbiting larger spirals has added another layer of complexity to our understanding of galaxy evolution. These small, faint galaxies often contain clues about the early stages of galaxy formation, as well as the effects of their interactions with larger systems. Some dwarf galaxies may even be remnants of larger systems that were stripped of their material through tidal interactions. Studying these satellites provides valuable insights into the hierarchical nature of galaxy formation and the role of environment in shaping the properties of spiral galaxies. As we move further into the study of spiral galaxies, the question of their ultimate fate becomes increasingly relevant. Over cosmic timescales, galaxies evolve in response to the changing conditions of the universe. For spiral galaxies, this evolution is shaped by a combination of internal processes, such as star formation and feedback, and external influences, such as interactions with other galaxies and the surrounding dark matter halo. While the specifics of this evolution vary from one galaxy to another, the overarching trend is a gradual transition from active, star-forming systems to more quiescent states. One possible endpoint for spiral galaxies is their transformation into lenticular galaxies, which exhibit features of both spirals and ellipticals. Lenticular galaxies typically lack the prominent arms of spiral galaxies and have lower rates of star formation, yet they retain a disk-like structure. This transformation can occur through processes such as the depletion of gas, the heating of the disk, or the stripping of material by interactions with other galaxies or the intracluster medium. The study of spiral galaxies is a testament to the dynamic and interconnected nature of the universe. These systems are not static but are constantly evolving, shaped by a complex interplay of forces and processes. Each new discovery adds a piece to the puzzle, revealing the intricate beauty and complexity of these cosmic structures. As our observational and theoretical tools continue to improve, we can look forward to uncovering even more of the secrets of spiral galaxies, deepening our understanding of the universe and our place within it. The future of spiral galaxies also raises questions about their role in the broader cosmic story. Their structures, behaviors, and interactions with other galaxies provide a lens through which we can observe the universe's history and its ongoing evolution. One particularly compelling aspect of this is how spiral galaxies contribute to the large-scale structure of the cosmos, including the web-like arrangement of galaxies and clusters that permeates space. Spiral galaxies are often found in groups and sometimes in larger clusters, but their environments vary significantly. In dense clusters, spirals are more likely to experience processes such as ram pressure stripping, where the hot gas of the intracluster medium removes the galaxy's cold gas, effectively halting star formation. This mechanism can transform a vibrant spiral into a quiescent lenticular or elliptical galaxy over time. Observing such transformations in action gives astronomers a window into how galaxies evolve based on their surroundings. The outermost reaches of spiral galaxies, often referred to as their halos, contain a wealth of information about these interactions. These halos are populated with extremely faint streams of stars and gas, remnants of smaller galaxies that were consumed or disrupted by the larger spiral. The detailed mapping of these streams, enabled by modern surveys like the Sloan Digital Sky Survey (SDSS) and the Gaia mission, has revealed complex patterns that testify to a galaxy's tumultuous past. By analyzing these features, astronomers can reconstruct the history of mergers, accretions, and other events that shaped the galaxy. Meanwhile, the gas that fuels star formation within spiral galaxies also holds significant clues about their evolution. The availability of gas varies widely among spirals, influenced by factors such as their environment, interactions with other galaxies, and feedback processes from active star formation or central black holes. Studying the reservoirs of gas in both local and distant spiral galaxies allows astronomers to understand how galaxies sustain their star formation over time, and what ultimately leads to its decline. For distant spiral galaxies, observing their gas and star formation provides a direct view into the early universe. Instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, allow astronomers to detect cold molecular gas in galaxies billions of light-years away, giving insight into the conditions that prevailed when the universe was younger. These observations have revealed that early spiral galaxies were often more turbulent and irregular than their modern counterparts, reflecting the chaotic environment of galaxy formation in the early cosmos. As we delve into the evolutionary history of spiral galaxies, the question of their initial formation becomes increasingly central. How did the first spiral galaxies emerge, and what processes led to the development of their characteristic features? Computer simulations, such as those conducted in the Illustris and Eagle projects, provide valuable insights by modeling galaxy formation and evolution on cosmological scales. These simulations suggest that spiral galaxies form through a combination of hierarchical assembly, where smaller structures merge to form larger ones, and the cooling and settling of gas into rotating disks. However, the exact mechanisms that lead to the formation of spiral arms remain an area of active research. While the density wave theory offers a compelling explanation for the persistence of these structures, alternative models such as swing amplification and tidal interactions provide additional perspectives. For example, some studies suggest that interactions with companion galaxies can induce spiral patterns, even in systems where internal density waves are not prominent. These competing theories highlight the complexity of spiral galaxy dynamics and the need for continued observations and simulations to refine our understanding. The role of spiral galaxies in the chemical evolution of the universe is another fascinating aspect of their story. Through the process of nucleosynthesis, stars within these galaxies produce heavy elements that are released into the interstellar medium during events such as supernova explosions and stellar winds. Over time, these elements become incorporated into new generations of stars, enriching the galaxy's overall metallicity. By studying the chemical composition of stars and gas in spiral galaxies, astronomers can trace the history of element formation and distribution across cosmic time. Interestingly, the chemical makeup of a galaxy also affects its ability to form planets, and potentially support life. Heavier elements are necessary for the formation of rocky planets like Earth, and their abundance in a galaxy can influence the likelihood of habitable worlds. Spiral galaxies, with their active star formation and relatively high metallicities, are thought to be particularly favorable environments for planet formation. This connection between the evolution of spiral galaxies and the potential for life adds a profound dimension to our study of these systems. Another intriguing question is how the diversity of spiral galaxies arises. Why do some spirals have grand, well-defined arms, while others exhibit flocculent or fragmented structures? Why do some spirals host prominent central bars, while others do not? The answers to these questions lie in the complex interplay of factors such as the galaxy's mass, rotation rate, and interaction history. For example, studies have shown that barred spirals are more common in older, more massive galaxies, suggesting that bars may form as a result of internal instabilities in the disk. The distribution of dark matter also plays a role in shaping the diversity of spiral galaxies. Simulations indicate that the density and shape of a galaxy's dark matter halo can influence the stability of its disk and the formation of spiral patterns. Observations of dark matter through techniques such as gravitational lensing and rotation curve analysis provide critical data for testing these theoretical predictions. As we push the boundaries of our knowledge, the future of spiral galaxy research holds immense promise. Next-generation telescopes, such as the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, are poised to revolutionize our understanding of these systems. These instruments will enable astronomers to observe faint, distant galaxies with unprecedented detail, shedding light on the earliest stages of spiral galaxy formation. They will also allow for more precise measurements of the properties of stars, gas, and dark matter in nearby spirals, deepening our understanding of their internal dynamics. One particularly exciting avenue of research is the study of spiral galaxies in the context of the cosmic microwave background, CMB. The CMB provides a snapshot of the universe shortly after the Big Bang, offering clues about the initial conditions that led to the formation of galaxies. By combining observations of spiral galaxies with data from the CMB, scientists can test theories of cosmic evolution and refine their models of galaxy formation. The story of spiral galaxies is far from complete. Each discovery raises new questions and challenges our assumptions, driving us to explore further. These elegant, dynamic systems are not only testaments to the beauty of the universe but also keys to understanding its deepest mysteries. From their graceful arms to their mysterious halos, spiral galaxies continue to captivate our imagination and inspire our quest for knowledge, reminding us of the boundless wonders of the cosmos. Spiral galaxies are also deeply intertwined with the larger narrative of cosmic evolution. Their interactions, transformations, and life cycles paint a vivid picture of the dynamism inherent in the universe. One fascinating aspect is how their evolution reflects the gradual buildup of structure across cosmic time. Early in the universe's history, when the first galaxies were forming, the conditions were markedly different from what we observe today. The density of the universe was higher, and interactions between galaxies were more frequent, leading to chaotic environments that influenced the development of early spiral galaxies. The formation of spiral galaxies often involves mergers and accretions, but not all such events disrupt their delicate disk structures. Minor mergers, where a spiral galaxy absorbs a smaller companion, can sometimes even enhance spiral features by triggering waves in the disk that reinforce the spiral pattern. However, major mergers, involving galaxies of comparable size, usually lead to the destruction of the disk and the formation of an elliptical galaxy. Understanding the balance between these processes is critical to reconstructing the evolutionary pathways of spiral galaxies. Another factor shaping spiral galaxies is their interaction with the intergalactic medium, IgM, the diffuse gas that fills the space between galaxies. As spiral galaxies move through this medium, particularly in dense environments like galaxy clusters, they can experience processes such as ram pressure stripping and harassment. These interactions can strip away gas, quench star formation, and even distort the galaxy's shape, leading to significant changes in its appearance and behavior. Observing these processes in real time provides a unique opportunity to study how galaxies respond to external forces. The study of spiral galaxies also offers a window into the mysterious role of supermassive black holes. Most, if not all, spiral galaxies are believed to harbor a supermassive black hole at their center, which can profoundly influence their evolution. These black holes can drive powerful outflows of gas and energy, known as active galactic nuclei (AGN), which regulates star formation by heating or expelling gas. The interplay between the central black hole and the rest of the galaxy is a key area of research, with implications for understanding how galaxies grow and change over time. Interestingly, the presence of bars in some spiral galaxies is thought to be connected to the activity of their central black holes. Bars can funnel gas toward the galaxy's core, fueling both star formation and black hole growth. Observations of barred spirals, therefore, provide valuable insights into the mechanisms that drive these processes and their impact on the galaxy as a whole. Additionally, the study of bar structures and their dynamics has revealed surprising complexities, such as the presence of double bars in some galaxies, where a smaller, secondary bar rotates within the primary bar. In terms of their role in the broader cosmic ecosystem, spiral galaxies are key contributors to the enrichment of the universe. The stars within these galaxies produce heavy elements through nuclear fusion, which are then released into the interstellar medium via supernova explosions and stellar winds. Over time, these elements become part of new stars, planets, and even life itself. The ongoing cycle of star formation and death within spiral galaxies drives the chemical evolution of the cosmos, making them crucial players in the story of how the universe has evolved to its current state. The study of spiral galaxies also touches on the nature of dark matter, an enigmatic substance that constitutes the majority of the universe's mass. Observations of spiral galaxy rotation curves, which plot the speed of stars and gas as a function of distance from the center, have provided some of the strongest evidence for dark matter. These curves remain flat or even rise at large radii, where the visible matter alone cannot account for the observed velocities. This discrepancy indicates the presence of an unseen mass component, which we now attribute to dark matter. Detailed studies of dark matter in spiral galaxies have revealed intriguing patterns. For instance, the distribution of dark matter often correlates with the galaxy's luminous components, suggesting a connection between the two. Some theories propose that interactions between dark matter and normal matter during the galaxy's formation could shape this relationship. Additionally, the study of dwarf galaxies, which are often satellites of larger spirals, provides further clues about dark matter's role in galaxy formation and evolution. Another area of active research is the study of spiral arms themselves. While the density wave theory provides a framework for understanding how these structures persist over time, recent observations and simulations have uncovered additional complexities. For example, the arms of some spiral galaxies appear to be more dynamic and transient than previously thought, forming and dissolving over relatively short timescales. This raises questions about the mechanisms that sustain these patterns and their relationship to the underlying disk dynamics. The relationship between spiral arms and star formation is also a subject of ongoing investigation. While it is clear that the arms are sites of active star formation, the precise connection between the two remains debated. Some studies suggest that the arms trigger star formation by compressing gas as they rotate through the disk, while others argue that the arms merely highlight regions where star formation is already occurring. Resolving this debate will require more detailed observations and simulations, particularly of the gas dynamics within spiral galaxies. Looking to the future, the study of spiral galaxies is set to benefit from a new generation of astronomical instruments and missions. The James Webb Space Telescope, JWST for example, is expected to provide unprecedented views of distant spiral galaxies, allowing us to study their formation and evolution in greater detail than ever before. Similarly, the Vera C. Rubin Observatory, with its wide-field survey capabilities, will map millions of galaxies, providing a comprehensive picture of the distribution and properties of spirals across the universe. The advent of advanced computational techniques is also revolutionizing the field. High-resolution simulations of galaxy formation and evolution, such as those conducted in the Illustris and Eagle projects, are providing new insights into the processes that shape spiral galaxies. These simulations incorporate a wide range of physical processes, from star formation and feedback to dark matter interactions, allowing researchers to test theories and make predictions that can be compared with observations. Ultimately, the study of spiral galaxies is not just about understanding these systems in isolation, but about placing them in the broader context of the universe's history. By unraveling the mysteries of their formation, evolution, and role in the cosmos, we gain a deeper appreciation for the complexity and interconnectedness of the universe. Spiral galaxies, with their graceful arms and vibrant star-forming regions, are a testament to the beauty and intricacy of the cosmos, reminding us of the countless mysteries that await discovery. The mysteries surrounding spiral galaxies don't just deepen our understanding of these celestial structures. They also challenge and refine the fundamental principles of astrophysics. One of the enduring questions in this field concerns the long-term stability of spiral patterns. If spiral arms are the result of density waves, as suggested by the density wave theory, why do some galaxies exhibit more well-defined and symmetrical arms, while others display fragmented or chaotic structures? This question remains central to understanding how spiral galaxies maintain their distinct appearance over billions of years. Simulations and observations suggest that spiral arms may be influenced by several factors working in tandem. These include the presence of nearby galaxies, the distribution of dark matter, and the internal dynamics of the galactic disk. In some cases, interactions with neighboring galaxies can induce tidal forces that enhance or even generate spiral patterns. For instance, when a smaller galaxy passes near or through a larger spiral galaxy, the gravitational interaction can trigger waves that propagate through the disk, amplifying or distorting the spiral structure. These tidal interactions are particularly evident in galaxies that exhibit a grand design spiral structure, those with well-defined and symmetrical arms. In contrast, flocculent spirals, which have more fragmented and irregular arm patterns, may form without significant external influences, relying instead on internal processes such as the self-gravity of gas clouds or localized star formation bursts. The distinction between grand design and flocculent spirals highlights the diversity of mechanisms that can shape these galaxies and underscores the complexity of their evolution. Another intriguing feature of spiral galaxies is their central bulge, which can vary dramatically in size and composition. Classical bulges, which resemble miniature elliptical galaxies, are thought to form through major mergers and rapid star formation events. In contrast, pseudobulges, which are flatter and more disk-like, appear to form through secular processes, gradual changes driven by the galaxy's internal dynamics. Understanding the relationship between a galaxy's bulge and its spiral arms provides valuable insights into its evolutionary history and the role of different formation processes. The interplay between the disk, bulge, and halo of a spiral galaxy is a critical area of research. The disk, which contains the spiral arms, is the site of ongoing star formation and the primary driver of the galaxy's luminous appearance. The bulge, by contrast, is typically dominated by older stars and plays a stabilizing role in the galaxy's structure. Surrounding both is the halo, an extended region of dark matter and sparse stellar populations that exerts a significant gravitational influence on the galaxy. Understanding how these components interact is essential for piecing together the full picture of spiral galaxy evolution. One particularly fascinating discovery is the presence of stellar streams in the halos of many spiral galaxies. These streams are remnants of smaller galaxies that were torn apart and absorbed by the larger spiral. By studying these streams, astronomers can reconstruct the history of past interactions and mergers, providing a kind of fossil record for the galaxy. This research has revealed that even galaxies that appear serene and stable today have often undergone tumultuous histories involving repeated interactions with their surroundings. In addition to their structure and dynamics, the chemical composition of spiral galaxies offers another layer of insight. The process of chemical enrichment, in which heavier elements are produced through stellar nucleosynthesis and distributed throughout the galaxy, is a key aspect of their evolution. Observations show that the metallicity of spiral galaxies, the abundance of elements heavier than hydrogen and helium, varies systematically across their disks. Typically, the metallicity decreases with distance from the center, reflecting the history of star formation and gas inflow in different regions. The distribution of gas in spiral galaxies is another critical factor in their evolution. While the visible stars dominate their appearance, the majority of the baryonic mass in spiral galaxies is in the form of gas, much of it invisible to optical telescopes. Radio observations have revealed vast reservoirs of neutral hydrogen gas in the outer regions of spirals, extending far beyond the visible disk. This gas serves as the raw material for future star formation and plays a crucial role in the galaxy's long-term evolution. The study of spiral galaxies also intersects with the broader field of cosmology, particularly in the context of galaxy formation and the large-scale structure of the universe. Spiral galaxies are not distributed randomly but are often found in groups and clusters, connected by vast filaments of dark matter and gas. This cosmic web structure reflects the influence of dark matter on the formation of galaxies, as well as the role of gas dynamics in shaping their properties. By studying the distribution and characteristics of spiral galaxies across the universe, astronomers can test theories about the formation of cosmic structure and the nature of dark matter. One of the most exciting areas of current research is the search for spiral galaxies in the early universe. With powerful telescopes like the James Webb Space Telescope, astronomers are beginning to observe galaxies that formed just a few 100 million years after the Big Bang. These early spirals provide a glimpse into the initial conditions that led to the formation of modern galaxies, offering clues about the processes that shaped their evolution. Observations of high redshift spirals have already challenged existing models, revealing unexpected complexities in their structure and composition. The future of spiral galaxy research is bright, with new technologies and techniques opening up unprecedented opportunities for discovery. Advanced simulations, incorporating detailed physics and spanning billions of years of cosmic time, are helping to unravel the mysteries of spiral galaxy formation and evolution. Observational campaigns, leveraging the capabilities of next-generation telescopes, are providing ever more detailed views of these galaxies, from their central bulges to their extended halos. Together, these efforts are painting a richer and more nuanced picture of spiral galaxies, shedding light on their role in the grand narrative of the universe. As we continue to explore the mysteries of spiral galaxies, we are reminded of the profound beauty and complexity of the cosmos. These majestic structures, with their graceful arms and vibrant star-forming regions, stand as a testament to the intricate interplay of forces that shape the universe. By studying spiral galaxies, we not only deepen our understanding of the cosmos but also uncover new questions and challenges, driving the quest for knowledge ever forward. The mysteries of spiral galaxies continue to captivate astronomers, not just because of their striking beauty but because they offer insights into the mechanisms shaping the universe. One particularly intriguing area of study involves the phenomenon of galactic migration within spiral galaxies. This refers to the movement of stars and gas across significant portions of the galaxy's disk over time. Such migration can blur the distinction between different regions of a galaxy, complicating efforts to reconstruct its evolutionary history. Galactic migration is often driven by the gravitational interactions within a spiral galaxy's disk. The spiral arms themselves, as density waves, create regions of higher gravity that can trap stars and gas, causing them to migrate inward or outward along the arms. This process can redistribute material across the galaxy, mixing older stars from the inner regions with younger ones from the outskirts. The result is a dynamic, evolving system where the past and present are interwoven in complex ways. The process of migration also affects the chemical composition of the galaxy. As stars move through the disk, they carry with them the elements they have synthesized, contributing to the chemical enrichment of new regions. This mixing process can help explain why the metallicity gradients observed in many spiral galaxies are not as steep as simple models might predict. It also highlights the interconnectedness of a galaxy's components, where the actions of individual stars can influence the larger structure. In addition to internal migration, spiral galaxies are shaped by external forces, particularly interactions with other galaxies. These interactions can range from subtle gravitational nudges to dramatic collisions and mergers, each leaving its mark on the galaxy's structure and evolution. For example, tidal forces from a close encounter can trigger waves of star formation, distort the spiral arms, or even create entirely new structures like tidal tails and bridges. These features provide direct evidence of the dynamic nature of galaxies and the ongoing processes that shape them. One of the most dramatic examples of external influence is the phenomenon of galactic cannibalism, where a larger galaxy absorbs a smaller one. In the context of spiral galaxies, such events can significantly alter their appearance and composition. The addition of new stars and gas can rejuvenate star formation in the spiral arms, while the gravitational disturbance can induce new patterns or amplify existing ones. Observations of galaxies like the Milky Way, which show evidence of past mergers, suggest that such events are a common and integral part of galactic evolution. The role of dark matter in shaping spiral galaxies is another area of active research. Although dark matter is invisible, its gravitational effects are essential for explaining the observed rotation curves of spiral galaxies. Without dark matter, the outer regions of spiral galaxies would not rotate as quickly as they do, and the galaxies themselves might not hold together. Dark matter halos, which extend far beyond the visible disk, provide the additional gravity needed to stabilize the galaxy and influence its structure. The distribution of dark matter also affects the formation of spiral arms. Simulations show that the density waves responsible for the arms can be influenced by the underlying dark matter halo, which shapes the overall gravitational potential of the galaxy. This interaction highlights the interplay between visible and invisible components, demonstrating that spiral galaxies are more than just the stars and gas we can see. Despite decades of study, many questions about spiral galaxies remain unanswered. For example, why do some galaxies transition from a spiral structure to an elliptical one? This transformation, often triggered by mergers or interactions, represents a fundamental change in the galaxy's dynamics and star formation activity. Understanding this process could shed light on the broader evolution of galaxies across cosmic time. Another mystery involves the diversity of spiral galaxy morphologies. Why do some spirals have tightly wound arms while others are more open? What determines the number of arms a galaxy has? While factors like rotation speed and the distribution of mass play a role, the exact mechanisms remain elusive. These questions underscore the need for further research and more sophisticated models. One promising avenue for future exploration is the study of spiral galaxies at different stages of their life cycles. By observing galaxies at various distances, and thus at different points in cosmic history, astronomers can piece together a timeline of their evolution. For example, younger spirals in the early universe might reveal the initial conditions that lead to the formation of arms, while older spirals in the local universe can provide clues about their long-term stability. Technological advancements are also driving new discoveries. Instruments like the James Webb Space Telescope and upcoming observatories will allow astronomers to study spiral galaxies in unprecedented detail. High-resolution imaging and spectroscopy will reveal the intricate interplay of stars, gas, and dark matter, providing deeper insights into the mechanisms that sustain spiral structures. The study of spiral galaxies is not just about understanding these specific objects, it's also about gaining insights into the broader processes that govern the universe. Spiral galaxies are a microcosm of cosmic dynamics, where the interplay of gravity, gas, and star formation creates structures of astonishing complexity. By studying them, we learn not only about the galaxies themselves but also about the forces that have shaped the cosmos as a whole. Ultimately, the fascination with spiral galaxies lies in their ability to inspire wonder and curiosity. They are not static or isolated entities but dynamic systems that reflect the intricate tapestry of the universe. From their swirling arms to their mysterious dark matter halos, spiral galaxies remind us of the beauty and complexity of the cosmos, inviting us to explore further and dream bigger. The exploration of spiral galaxies also provides a window into the processes that govern the birth and death of stars. Within the spiral arms, regions of intense star formation are often observed, with clouds of gas and dust collapsing under gravity to form new stars. These areas, known as H2 regions, are the cradles of stellar birth. The gas in these regions is ionized by the ultraviolet radiation emitted by young, hot stars, causing it to glow brightly and reveal its presence to astronomers. Interestingly, these regions of star formation are often found in the outer regions of the spiral arms, where gas density is higher. This further reinforces the idea that the spiral arms are not static features but are in constant flux, influenced by the density waves moving through the galaxy. As these waves pass through the gas clouds in the arms, they compress the material, triggering the formation of new stars. The cycle of star birth and death in the spiral arms plays a significant role in shaping the galaxy's overall composition, enriching the surrounding space with heavier elements through supernovae and stellar winds. While the birth of new stars is an exciting aspect of spiral galaxies, their evolution is equally marked by the death of old ones. Over time, as stars in the central bulge and in the spiral arms exhaust their nuclear fuel, they will evolve into white dwarfs, neutron stars, or even black holes. The end stages of a star's life are crucial in determining the fate of a galaxy. For instance, a massive star that ends its life in a supernova explosion can send shockwaves through the surrounding gas, triggering further star formation in the process. On the other hand, stars that evolve into white dwarfs or black holes contribute to the galaxy's gravitational field, influencing the motion of other stars and material within the galaxy. In addition to stellar processes, spiral galaxies undergo a complex interaction with their surrounding environment. These interactions range from the gravitational effects of nearby galaxies to the influence of the intergalactic medium. Galaxies in clusters, for instance, often experience ram pressure stripping, a process in which the gas in a galaxy's disk is stripped away by the pressure exerted by the hot gas present in the cluster. This process can lead to a significant reduction in the galaxy's ability to form new stars, as it depletes the raw materials necessary for star formation. In contrast, galaxies in more isolated environments can maintain their gas reservoirs for longer periods, allowing them to continue forming stars at a steady rate. However, even isolated spiral galaxies are not immune to external influences. Over time, gravitational interactions with other galaxies can lead to a process known as galactic harassment, where the galaxy's structure is distorted, and its gas is redistributed, potentially triggering a new round of star formation or leading to the eventual shutdown of star formation altogether. The study of gas inflows into spiral galaxies has also revealed fascinating insights into their evolution. Recent research suggests that many spiral galaxies, including our own Milky Way, continue to accrete gas from the intergalactic medium. This process, known as cold mode accretion, is thought to be responsible for replenishing the gas reservoirs of galaxies, enabling them to maintain star formation over long periods. This ongoing influx of gas helps to sustain the spiral structure of galaxies, providing the necessary material for both the formation of new stars and the maintenance of existing stellar populations. One of the most intriguing discoveries in recent years is the role of black holes in the evolution of spiral galaxies. At the center of most spiral galaxies, including the Milky Way, lies a supermassive black hole. The influence of supermassive black holes on their host galaxies is a key aspect of the evolution of spiral galaxies. These black holes, often millions or even billions of times the mass of the Sun, are thought to regulate galactic activity through a process known as feedback. When material falls into a supermassive black hole, it heats up and emits large amounts of radiation, which can have profound effects on the surrounding gas and stars. In some cases, this radiation can be so intense that it drives powerful outflows, or winds, that push gas away from the galaxy's center. These outflows can halt star formation by stripping away the very gas needed to form new stars. This feedback mechanism has a delicate balance. If the outflows are too strong, they can inhibit star formation altogether, leading to a more passive, older galaxy. On the other hand, if the feedback is insufficient, the galaxy may continue to form stars at an unsustainable rate, depleting its gas supply too quickly. This dynamic process helps to explain why many spiral galaxies, especially those with active galactic nuclei, show evidence of both star formation and suppression happening simultaneously. Furthermore, The supermassive black hole's gravity can have a subtle but significant impact on the morphology of the galaxy itself. The gravitational influence of these black holes can help to shape the bulge at the center of a spiral galaxy. Over time, as stars and gas spiral inward toward the black hole, they can contribute to the growth of the bulge, which is a critical structural component of spiral galaxies. In some cases, interactions between the central black hole and the surrounding stars can even trigger the formation of new structures, such as bar-like features, which further complicate the dynamics of the galaxy's arms. It's not just the black holes that contribute to the evolution of spiral galaxies, but the entire environment of a galaxy. For instance, the so-called galactic halo, a spherical region of dark matter that surrounds spiral galaxies, plays a critical role in the overall gravitational framework of the galaxy. This halo influences the rotation curves of galaxies, contributing to the phenomenon where the outer regions of galaxies rotate faster than expected. The dark matter that makes up the bulk of the halo is invisible to us, yet its gravitational effects can be observed in the movement of stars and gas in the outer regions of spiral galaxies. This halo of dark matter not only helps to keep the galaxy intact but also plays a role in the evolution of the galaxy's spiral structure. Simulations have suggested that the gravitational influence of the dark matter halo can help to stabilize the spiral arms, ensuring that they don't dissipate over time. Additionally, dark matter might influence the way that spiral galaxies interact with their environment. For example, a galaxy moving through a cluster of other galaxies might experience changes in its dark matter halo, leading to altered dynamics in the spiral arms or the galaxy's overall structure. The relationship between the spiral arms and the galactic center is another area of interest for astronomers. Traditionally, spiral galaxies were thought to have a simple, well-defined spiral structure, with arms extending outward from the center like the spokes of a wheel. However, recent observations have revealed that spiral arms are more dynamic than previously imagined. They are not fixed structures, but rather are shaped by waves of density that propagate through the galaxy's disk. These waves cause gas and stars to clump together, forming the characteristic arms of a spiral galaxy. Interestingly, the arms of a spiral galaxy are not always evenly spaced or symmetric. Some galaxies exhibit tightly wound arms, while others have more loosely wound or even irregularly shaped arms. These differences may arise from variations in the galaxy's mass distribution, rotation, or interactions with nearby galaxies. The Milky Way, for instance, has relatively loose spiral arms, while galaxies like the Andromeda Galaxy feature more tightly wound arms. This variability suggests that the formation of spiral arms is influenced by a complex interplay of factors, including the galaxy's intrinsic properties and external influences. One fascinating question that remains largely unanswered is why spiral galaxies tend to form with a specific number of arms. While most spiral galaxies have 2 arms, some galaxies exhibit more, and a few appear to have only 1. The number of arms in a spiral galaxy can be influenced by factors such as the galaxy's rotation speed, the distribution of gas and stars, and interactions with other galaxies. In some cases, galaxies with multiple arms may undergo a process known as multiple arm winding, where the arms grow closer together over time, forming a tightly wound structure. The transition from a spiral galaxy to other types of galaxies, particularly elliptical galaxies, is another area of intense research. While spiral galaxies are known for their active star formation and complex structures, elliptical galaxies are typically characterized by a lack of spiral arms and a more homogeneous distribution of stars. Understanding the mechanisms behind this transformation is crucial for understanding the long-term evolution of galaxies. Mergers between spiral galaxies and other types of galaxies are thought to play a key role in this process. When 2 spiral galaxies collide, their gas and stars can become heavily disrupted, leading to the eventual cessation of star formation and the formation of a more spheroidal shape. In some cases, this results in the creation of an elliptical galaxy. The transformation of a spiral galaxy into an elliptical one represents a fundamental shift in the galaxy's dynamics, from a system of active star formation to one dominated by older stars and a more passive state. As we look to the future of spiral galaxy research, the development of advanced astronomical instruments holds great promise for uncovering new mysteries. Telescopes like the James Webb Space Telescope and future ground-based observatories will allow astronomers to peer deeper into the heart of spiral galaxies than ever before. By studying the composition, structure, and dynamics of spiral galaxies across different cosmic epochs, scientists hope to uncover new insights into their formation, evolution, and ultimate fate. Spiral galaxies continue to be a central focus of astrophysical research, offering a wealth of information about the nature of galaxies, the universe, and the forces that shape them. From their mesmerizing arms to their enigmatic dark matter halos, spiral galaxies remain one of the most captivating and mysterious structures in the cosmos. And as our understanding deepens, we are bound to uncover even more about these fascinating systems, giving us a greater appreciation of the intricate workings of the universe. As we delve further into the mysteries of spiral galaxies, it's important to consider the role of cosmic environments in shaping their evolution. The large-scale structure of the universe plays a fundamental part in determining the trajectory of a spiral galaxy's development. Galaxies are not isolated entities. They are part of vast cosmic structures, ranging from smaller groups to enormous clusters of galaxies. These clusters, in particular, exert significant gravitational influence, affecting the motion, shape, and star formation processes of the spiral galaxies within them. For example, galaxies within a cluster often experience interactions that can lead to modifications in their structure. When a spiral galaxy enters a dense cluster, it may encounter its neighbors in ways that trigger changes in its spiral arms or even result in the stripping of its gas and dust, halting the formation of new stars. The high-speed collisions between galaxies can result in dramatic mergers, leading to the creation of elliptical galaxies or irregular galaxies, which no longer exhibit the familiar spiral structure. This transformation is another crucial aspect of the life cycle of spiral galaxies and underscores the importance of galactic environments in determining the fate of these systems. On a more local scale, spiral galaxies can also be shaped by tidal interactions. When a spiral galaxy passes close to another galaxy, the gravitational forces between the two can distort the shape of the galaxy, stretching it out, or even disrupting its spiral arms. These interactions can lead to the transfer of gas and stars between galaxies, triggering bursts of star formation or, in some cases, depleting the galaxy's gas supply entirely. The tug-of-war between galaxies during tidal interactions can be subtle, but over millions or billions of years, it can dramatically alter the structure and evolution of a spiral galaxy. Interestingly, the study of nearby galaxies also provides insights into the evolution of our own Milky Way. By examining galaxies similar to the Milky Way, astronomers can gain a better understanding of the processes that have shaped our galaxy's spiral structure and the role that various cosmic phenomena have played in its development. Observing the Milky Way's neighbors allows scientists to study the stages of spiral galaxy evolution in real time, offering clues about the future evolution of our galaxy. One of the most fascinating aspects of spiral galaxies is their resilience. Despite undergoing various external and internal changes throughout their long histories, spiral galaxies are remarkably enduring structures. This resilience is partly due to the dynamics of their rotation, the steady flow of gas, and the constant cycle of star formation and death that takes place within their spiral arms. Even in the face of galaxy mergers, tidal forces, and environmental stresses, spiral galaxies can continue to thrive and evolve, adapting to their changing surroundings. This longevity challenges our understanding of the lifespan of galaxies and their ability to maintain such intricate and beautiful structures over billions of years. In addition to the more familiar spiral arms, it's essential to examine the role of bars within spiral galaxies. Many spiral galaxies, including the Milky Way, exhibit a central bar-like structure that runs through the galactic core. These bars are thought to be the result of gravitational forces acting on the stars and gas in the central region of the galaxy. The exact formation mechanism for bars is still a subject of study, but it is widely believed that they may arise from the redistribution of material due to the galaxy's overall gravitational dynamics. Bars play a crucial role in the evolution of spiral galaxies. They can act as a funnel, channeling gas toward the galaxy's center. This influx of material can fuel both the formation of new stars and the growth of the supermassive black hole at the galaxy's core. In some cases, bars may also help to stabilize the galaxy's spiral structure, maintaining the integrity of the arms by controlling the flow of gas and stars through the disk. The presence of a bar can dramatically alter the dynamics of a spiral galaxy, influencing star formation rates, the distribution of gas, and even the shape of the spiral arms themselves. However, not all spiral galaxies possess prominent bars. In fact, many spiral galaxies, including some of our closest neighbors, are classified as unbarred spirals. The lack of a bar in these galaxies raises interesting questions about the variety of mechanisms that can lead to the formation and maintenance of spiral structures. Whether or not a spiral galaxy develops a bar could be influenced by factors such as the galaxy's mass, the rate of star formation, and the interplay of gravitational forces between the galaxy and its environment. These distinctions between barred and unbarred spiral galaxies highlight the complexity of the processes at play in the formation and evolution of spiral galaxies. Another intriguing aspect of spiral galaxies is the presence of their dark matter halos. Dark matter, which constitutes roughly 27% of the universe's mass energy content, is a mysterious substance that does not emit, absorb, or reflect light, making it invisible to conventional telescopes. Despite its elusive nature, astronomers have inferred the existence of dark matter by studying its gravitational effects on visible matter. In the case of spiral galaxies, dark matter is thought to reside in a halo that extends far beyond the visible disk of the galaxy. This dark matter halo is essential for explaining the galaxy's observed rotation curve, which shows that stars in the outer regions of spiral galaxies move much faster than expected based on the visible matter alone. The presence of dark matter influences the entire dynamics of spiral galaxies. It is believed that dark matter helps to maintain the structural integrity of the galaxy by providing the additional gravitational pull necessary to prevent the galaxy from flying apart. Without dark matter, spiral galaxies would likely be unable to maintain their spiral structure over long periods of time. The discovery of dark matter has had profound implications for our understanding of galaxy formation and evolution, prompting further research into the properties and behavior of this mysterious substance. Recent advancements in technology, such as the development of powerful ground-based telescopes and space observatories, have allowed scientists to probe deeper into the structure of spiral galaxies than ever before. Instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the James Webb Space Telescope are providing unprecedented views of the gas and dust in spiral galaxies, allowing astronomers to study the intricate details of their star formation processes, gas dynamics, and interactions with other galaxies. These advancements are helping to unravel some of the most enduring mysteries of spiral galaxies, bringing us closer to understanding their complex origins and evolution. Spiral galaxies are not just beautiful and captivating structures. They are dynamic systems that are shaped by a wide array of cosmic forces. From the birth and death of stars in the spiral arms to the influence of dark matter and supermassive black holes, the evolution of spiral galaxies is a complex and ongoing process. These galaxies provide a window into the larger workings of the universe, offering clues about the fundamental processes that govern the formation and evolution of galaxies across cosmic time. While much has been learned, there is still much more to discover about these enigmatic structures, and as our tools and understanding improve, we will undoubtedly uncover even more about the evolution of spiral galaxies and their place in the vast expanse of the cosmos. The mysteries surrounding spiral galaxies continue to captivate the minds of scientists and stargazers alike. As we push the boundaries of observational technology and theoretical models, we uncover more layers of complexity in the structure and evolution of these galaxies. One of the most important factors influencing spiral galaxies is the rate of star formation, which not only affects their appearance but also their lifespan and evolution. Understanding how and why certain regions of spiral galaxies are more prolific in star formation than others has been a key focus in astronomy. Star formation within spiral galaxies is a fascinating process that takes place primarily in the spiral arms. These arms, composed of vast clouds of gas and dust, are the sites where new stars are born. The arms themselves are not permanent structures. Rather, they are density waves traveling through the galaxy, compressing the gas and dust as they move. When this gas is compressed, it triggers the formation of new stars, giving rise to regions of intense brightness. The spiral arms, in essence, act like factories for stellar creation. However, not all parts of a spiral galaxy experience the same level of star formation. The central bulge, which is the dense region at the heart of many spiral galaxies, typically exhibits much lower star formation rates. This area is dominated by older stars, and it is often where the supermassive black hole resides. The bulge of a spiral galaxy can exert significant gravitational influence on its surrounding disk, affecting the flow of gas and the dynamics of the entire system. The balance between the gas-rich spiral arms and the gas-poor central bulge is one of the key factors that shapes the overall morphology and evolution of the galaxy. Interestingly, the outer regions of spiral galaxies, often referred to as the galactic halo, also play a crucial role in the galaxy's evolution, though they are not as visible as the bright spiral arms. The halo is composed of stars, gas, and dark matter, and it extends well beyond the visible disk of the galaxy. While the halo is not a major site of star formation, it contains important information about the galaxy's history. In many ways, the halo represents the remnants of earlier stages in the galaxy's evolution, and it can offer clues about the processes that led to the formation of the galaxy itself. In addition to the study of star formation, the investigation of the interactions between spiral galaxies and their environments has proven to be a rich area of research. As spiral galaxies move through the cosmic landscape, they interact with neighboring galaxies and the intergalactic medium in profound ways. These interactions can lead to the exchange of gas and stars, the triggering of new star formation, or, conversely, the stripping away of material from the galaxy. In some cases, galaxies may collide with each other, causing their structures to merge or distort. These mergers can transform spiral galaxies into elliptical galaxies, a process that is still not fully understood but is central to the evolution of galaxies in the universe. One of the most notable phenomena associated with galaxy collisions is the creation of active galactic nuclei, AGN. AGNs are regions of intense energy and activity that often appear at the centers of galaxies, particularly in those that have recently undergone a merger. These regions are powered by the supermassive black hole at the galaxy's core, which is actively accreting material. As material falls into the black hole, it heats up, emitting vast amounts of radiation that can outshine the rest of the galaxy. AGNs are thought to play a key role in regulating the growth and evolution of galaxies, and their study provides insights into the interplay between galaxies and the supermassive black holes that reside at their centers. The discovery of the relationship between spiral galaxies and their supermassive black holes has been one of the most significant breakthroughs in astrophysics. It is now understood that nearly every large galaxy, including spiral galaxies like the Milky Way, harbors a supermassive black hole at its core. These black holes, which can have masses millions or even billions of times that of the Sun, have a profound effect on their host galaxies. The accretion of matter by these black holes can generate enormous amounts of energy, influencing star formation rates and the overall dynamics of the galaxy. However, the exact role of supermassive black holes in the evolution of spiral galaxies remains an open question. Some scientists believe that the energy released by the black hole may help regulate star formation in the galaxy by heating the surrounding gas, preventing it from collapsing to form new stars. Others suggest that the black hole's influence may extend beyond the galaxy itself, affecting the intergalactic medium and the surrounding galaxy cluster. The ongoing study of supermassive black holes and their interaction with their host galaxies is a critical area of research that will continue to shape our understanding of galaxy evolution in the coming decades. Moreover, one of the most exciting aspects of spiral galaxies is their potential for hosting habitable planets. As we study exoplanets in the Milky Way and beyond, it becomes clear that spiral galaxies, with their abundant gas and dust, provide an ideal environment for the formation of planets. The presence of heavy elements, which are essential for the creation of planets and life as we know it, is particularly common in the disks of spiral galaxies. This raises the intriguing possibility that spiral galaxies are not only sites of stellar and galactic evolution, but also places where life may exist elsewhere in the universe. The search for habitable planets and spiral galaxies has intensified with the advent of new observational tools, such as the Kepler Space Telescope and the James Webb Space Telescope. These instruments have revolutionized our understanding of exoplanets by allowing us to detect planets in the habitable zone of distant stars, regions where conditions may be suitable for liquid water to exist. As we continue to explore the potential for life in spiral galaxies, we may one day find that we are not alone in the universe, and that spiral galaxies, with their rich mix of stars, gas, and planets, could be the birthplace of life elsewhere. Looking forward, the study of spiral galaxies will continue to evolve as our technology improves and our understanding of the universe deepens. New telescopes, observatories, and computational models will provide us with increasingly detailed images of spiral galaxies, allowing us to peer further into their cores and study the intricate processes at play in their evolution. With each new discovery, we move closer to understanding the fundamental forces that shape galaxies and the cosmos as a whole. Whether it's the formation of spiral arms, the influence of dark matter, or the role of supermassive black holes, the evolution of spiral galaxies remains one of the most captivating mysteries of modern astronomy. Spiral galaxies represent some of the most complex and dynamic systems in the universe. From their formation and the processes that drive their evolution to their interactions with other galaxies and the cosmic structures around them, spiral galaxies continue to challenge our understanding of the universe. Their beauty, complexity, and resilience make them an endless source of fascination for astronomers, and with each new breakthrough, we gain deeper insights into the forces that shape not only galaxies but the very fabric of the cosmos itself. As we continue to investigate the evolution of spiral galaxies, one of the key areas of interest is the role that galactic interactions and mergers play in shaping the destiny of these celestial structures. While the classic image of a spiral galaxy often portrays it as a peaceful, isolated entity, the reality is that these galaxies are rarely static. They are constantly evolving due to both internal dynamics and external forces. When galaxies collide or pass through each other, they can undergo dramatic transformations, often resulting in the disruption of their spiral structure. The first step in understanding how interactions affect spiral galaxies is to consider the sheer scale of the forces involved. Galaxies are vast, and the gravitational pull between them is immense. When two spiral galaxies encounter one another, the gravitational attraction can cause tidal forces to warp the galaxy's shapes, stretch their arms, and disrupt their regular motion. These interactions can lead to significant changes in the star formation rate and the distribution of gas and stars within the galaxies. In some cases, the collision might even strip away large portions of the galaxy's outer regions, potentially leading to the creation of an entirely new structure. While mergers between spiral galaxies can sometimes lead to the formation of elliptical galaxies, not all galactic interactions have such drastic outcomes. Some spiral galaxies may simply pass through one another, their spiral arms temporarily distorted by the tidal forces, only to return to their previous state once the encounter has passed. However, even these less dramatic encounters can still have lasting effects on the galaxy's evolution. For instance, the gravitational interaction may funnel gas toward the center of the galaxy, sparking new waves of star formation, or, conversely, it may lead to the suppression of star formation as the gas is removed or redistributed. One of the most fascinating phenomena that arise from galaxy mergers is the formation of starbursts. A starburst is a period of extremely high star formation that can occur when two galaxies collide or interact. The interaction can compress gas clouds, triggering the formation of large numbers of stars in a relatively short time. This burst of star formation can give rise to bright, luminous regions within the galaxy, sometimes outshining the galaxy's core. Starbursts can also dramatically alter the chemical composition of the galaxy, as the newly formed stars release heavy elements into the interstellar medium, enriching the galaxy's gas and dust. In addition to starbursts, the gravitational forces during a galaxy merger can trigger the formation of a bar structure at the center of the galaxy. Bars are elongated regions of stars that can form in the center of spiral galaxies, often altering the dynamics of the galaxy's disk. While some bars are short-lived and may disappear after a few 100 million years, others can persist for much longer, playing a critical role in the transport of gas and stars within the galaxy. Bars can funnel gas toward the central regions of a galaxy, fueling both star formation and the growth of the supermassive black hole at the galaxy's core. This process is particularly important in the evolution of galaxies, as it can regulate the rate of star formation and the growth of the galaxy's central black hole. As spiral galaxies continue to evolve, one of the most profound questions in astrophysics is how the dark matter that surrounds these galaxies influences their structure and behavior. Dark matter, which makes up approximately 85% of the mass in the universe, is invisible and cannot be directly observed through traditional means. However, its presence is inferred by its gravitational effects on visible matter. In the case of spiral galaxies, dark matter is thought to form a large, spherical halo surrounding the galaxy, influencing the rotation of the galaxy and its overall dynamics. The exact role of dark matter in the evolution of spiral galaxies remains a topic of intense study. Some theories suggest that dark matter may play a critical role in stabilizing the galaxy's spiral arms, preventing them from collapsing or dispersing. Others propose that dark matter may act as a galactic glue, binding the galaxy's stars and gas together, and helping to shape the overall structure of the galaxy. Regardless of its exact role, dark matter is undoubtedly a crucial component of spiral galaxies, and understanding its properties is essential for unlocking the secrets of galactic evolution. Another aspect of spiral galaxy evolution that has garnered increasing attention in recent years is the role of gas and dust in the formation of spiral arms and the regulation of star formation. While stars are the most visible component of a galaxy, gas and dust are equally important in shaping its structure and evolution. Gas clouds serve as the raw material for star formation, and the distribution of gas within a galaxy can have a significant impact on its spiral structure. For instance, regions of higher gas density tend to form the bright, luminous arms of spiral galaxies, while areas with less gas may form the dark regions in between. The complex interplay between gas, dust, and stars in a spiral galaxy is still not fully understood, but recent advances in observational technology are beginning to shed light on these processes. By studying the motion of gas within galaxies, astronomers have been able to model the behavior of spiral arms and gain insight into the forces that govern their formation and evolution. For example, simulations suggest that spiral arms are not static structures but rather dynamic waves of gas and stars that move through the galaxy over time. These waves, driven by gravitational interactions and the motion of stars, create the characteristic spiral shape that defines these galaxies. The behavior of gas within spiral galaxies is also influenced by the presence of supermassive black holes at their centers. As we mentioned earlier, these black holes can exert a powerful gravitational pull on their surroundings, affecting the flow of gas and stars within the galaxy. In some cases, the black hole may even drive outflows of gas, suppressing star formation and altering the galaxy's evolution. These outflows, often referred to as active galactic nuclei, or AGN feedback, can have a profound effect on the galaxy's structure and its ability to form new stars. At the same time, the inflow of gas into the central regions of the galaxy can fuel the growth of the supermassive black hole, potentially leading to the formation of an active galactic nucleus. These regions of intense radiation, powered by the accretion of gas onto the black hole, can emit enormous amounts of energy, sometimes outshining the galaxy's entire disk. AGN feedback, however, is a double-edged sword. It can regulate the growth of the galaxy by suppressing star formation, but it can also lead to the depletion of gas, stalling the formation of new stars. This delicate balance between gas inflow and outflow plays a crucial role in determining the future evolution of spiral galaxies. The process of galaxy evolution is not only influenced by internal forces but also by the larger-scale cosmic environment. Spiral galaxies are rarely isolated. They are part of galaxy clusters and groups, where they interact with other galaxies and the intergalactic medium. The dense environment of a galaxy cluster can have a profound effect on a spiral galaxy, causing it to lose gas and stars through processes such as ram pressure stripping and tidal interactions. These interactions can alter the spiral galaxy's shape, slow down its star formation, or even transform it into a different type of galaxy altogether. One of the most fascinating aspects of this broader galactic environment is the discovery of intracluster light. This diffuse glow, which emanates from the combined light of stars that have been stripped from galaxies within a cluster, provides valuable information about the processes occurring in these cosmic neighborhoods. By studying intracluster light, astronomers can gain insights into the dynamics of galaxy clusters and the interactions between galaxies that drive their evolution. As we look ahead to the future, the study of spiral galaxies will undoubtedly continue to be a cornerstone of astronomical research. New technologies, such as the upcoming James Webb Space Telescope, will provide unprecedented views of distant spiral galaxies, enabling scientists to study their structures and evolution in greater detail than ever before. The mysteries of spiral galaxies, how they form, how they evolve, and how they interact with their environment, are far from solved, but with each new discovery, we move closer to understanding the complex and fascinating story of these galaxies. As we venture further into the evolution of spiral galaxies, one important aspect that remains to be fully understood is the role of galaxy halos. These halos, which consist of stars, gas, and dark matter, extend far beyond the visible disk of the galaxy, often accounting for a significant portion of the galaxy's total mass. The nature of galaxy halos, especially their dark matter component, has profound implications for our understanding of galactic formation and evolution. Dark matter halos are believed to be the primary structures that shape the gravitational well of a galaxy, determining how galaxies form and evolve over billions of years. Dark matter's gravitational pull not only helps to hold galaxies together but also influences the rotation of the galaxy, particularly in the outer regions where the visible stars and gas are less concentrated. The presence of dark matter in the halo prevents spiral galaxies from flying apart, as the visible mass of stars alone is not sufficient to explain the observed rotation curves of galaxies. This discrepancy between visible matter and the observed gravitational pull led to the original discovery of dark matter, and it continues to be a critical aspect of galactic research. Moreover, the evolution of the halo is intertwined with the galaxy's growth and the formation of its spiral structure. During the early stages of a galaxy's life, the halo plays a crucial role in accreting gas and other material, providing the raw ingredients for the formation of stars. Over time, the interaction between the halo and the galaxy's disk can lead to the exchange of gas, with the halo potentially supplying material that is funneled into the disk, triggering new rounds of star formation. This feedback loop between the halo and the disk is thought to be a key factor in determining the long-term evolution of the galaxy. Additionally, the dark matter halo can influence the formation and persistence of spiral arms. These arms are often thought to arise from density waves, regions of higher mass and gravitational influence that spiral outward from the center of the galaxy. The presence of dark matter can help stabilize these arms, ensuring that they persist over long periods of time. Without the support of the halo's dark matter, the spiral structure of a galaxy might become less defined and more prone to disruption. As we explore the future of spiral galaxies, it's essential to consider the role of galactic evolution on cosmic timescales. The future of any spiral galaxy is shaped by a combination of its internal dynamics and its interactions with other galaxies and the larger cosmic environment. Over billions of years, the balance between star formation and galactic mergers will continue to drive the evolution of spiral galaxies, potentially leading to their transformation into elliptical galaxies or other types of galactic structures. The eventual fate of the Milky Way, our own spiral galaxy, provides a fascinating glimpse into the long-term evolution of these celestial objects. The Milky Way is currently on a collision course with the Andromeda Galaxy, the nearest large spiral galaxy. This collision, which is expected to occur in about 4.5 billion years, will likely result in the merger of the two galaxies. While the exact outcome of this merger is still uncertain, it's expected that the spiral structure of both galaxies will be significantly altered, and they may eventually form a new, larger elliptical galaxy. The merger of galaxies is not an unusual event in the cosmic timeline. Throughout the history of the universe, galaxies have collided and merged with one another, leading to dramatic transformations in their shapes and structures. These collisions are an essential part of galactic evolution, as they often lead to the redistribution of stars, gas, and dark matter, reshaping the galaxies involved. For spiral galaxies, these mergers can have profound effects on their spiral arms, star formation rates, and central black hole activity. In addition to the physical interactions that occur during mergers, the larger cosmic environment in which galaxies reside also plays a crucial role in their evolution. The large-scale structure of the universe is made up of galaxy clusters and superclusters, with galaxies bound together by gravity. Within these clusters, galaxies often interact with one another, exchanging gas and stars, and sometimes undergoing more violent interactions like galaxy cannibalism. This process, in which one galaxy absorbs another, can lead to the formation of elliptical galaxies, as the spiral arms of the smaller galaxy are disrupted and the galaxy's stars are redistributed. While mergers and interactions with other galaxies can be disruptive to a spiral galaxy structure, they also present opportunities for growth. Over cosmic timescales, mergers can lead to the formation of larger galaxies with more complex structures. In fact, many of the largest galaxies in the universe today are the result of multiple mergers that have occurred over billions of years. The question of whether spiral galaxies will continue to evolve into even larger and more complex structures remains a subject of ongoing research. One exciting avenue of exploration involves the study of galactic feedback. Galactic feedback refers to the processes by which a galaxy's activity, particularly in the form of star formation, black hole accretion, and supernova explosions, can influence its environment. These processes can drive gas outflows, alter the galaxy's gas supply, and regulate the rate of star formation. Galactic feedback is crucial in understanding the evolution of spiral galaxies, as it can either stimulate or suppress the formation of new stars. This feedback loop is responsible for much of the complex interplay between a galaxy's star formation, its supermassive black hole, and the surrounding intergalactic medium. The study of galactic feedback is still in its early stages, but it has already led to several groundbreaking discoveries. For example, recent observations have revealed that the supermassive black holes at the centers of galaxies can produce powerful jets of energy and matter, which can extend far beyond the galaxy itself. These jets can heat the surrounding gas, preventing it from cooling and collapsing to form new stars. In some cases, this feedback can completely shut down star formation in a galaxy, leading to a red and dead galaxy that is devoid of young stars. The role of magnetic fields in spiral galaxies is also an important aspect of their evolution. While we often think of magnetic fields as being confined to planets or stars, galaxies themselves possess vast magnetic fields that can influence the motion of gas and stars. These fields can play a role in shaping the spiral arms of galaxies, as well as in regulating the flow of gas and the formation of new stars. Magnetic fields can also have a significant impact on the behavior of supernovae, and the energy output of supermassive black holes, adding another layer of complexity to the already intricate process of galactic evolution. As we look ahead, the study of spiral galaxies will continue to be a central focus in the field of astronomy. With new technologies, like the James Webb Space Telescope, scientists will be able to peer deeper into the universe than ever before, observing galaxies at various stages of their evolution. These observations will provide invaluable insights into the processes that drive the formation and evolution of spiral galaxies, shedding light on everything from star formation to dark matter. The evolution of spiral galaxies is a story that spans billions of years, shaped by a combination of internal dynamics, external interactions, and cosmic-scale forces. From their formation in the early universe to their future collisions and mergers, spiral galaxies are constantly evolving, providing us with a fascinating window into the workings of the universe. As our understanding of these galaxies continues to grow, we move closer to unraveling the mysteries of galactic evolution and the forces that shape the cosmos itself. The quest to understand spiral galaxies also leads us to explore the key components that make up their distinct features. These features, such as spiral arms, bulges, and the galactic disk, are not just visually striking but are essential to the very structure and dynamics of these galaxies. By examining each component in more detail, we can gain insight into how they evolve over time and how they interact with the surrounding environment. One of the most intriguing features of spiral galaxies is their spiral arms. These arms are not static structures, but rather dynamic features that evolve over time. They are often described as density waves, regions of higher mass concentration that move outward from the galactic center. These density waves cause the stars and gas in the galaxy to move in a way that reinforces the spiral structure. The spiral arms are a product of the galaxy's internal gravitational forces, but they can also be influenced by external forces, such as interactions with nearby galaxies or the gravitational pull of dark matter. The formation of spiral arms is linked to the rate of star formation in a galaxy. The density waves that form the arms compress the gas and dust within the galaxy, leading to the creation of new stars. This process is often referred to as starburst activity. In the arms of a spiral galaxy, we often find young, blue stars, which are much hotter and more luminous than older stars. These young stars are born from the dense regions of gas that are compressed by the density waves, giving the spiral arms their characteristic bright, blue appearance. While spiral arms are a defining feature of spiral galaxies, they are not the only important component. The central bulge of a spiral galaxy is another key feature that plays a significant role in its evolution. The bulge is a dense concentration of stars that sits at the core of the galaxy, and it can vary in size and shape depending on the galaxy. In some galaxies, the bulge is a smooth, spherical structure, while in others, it may be elongated or slightly flattened. The formation of the bulge is closely linked to the history of the galaxy itself. It is believed that the bulge forms through a combination of processes, including the collapse of gas during the early stages of galaxy formation and the accumulation of stars from various sources over time. The bulge is often home to a supermassive black hole, which can have a profound effect on the surrounding region. The activity of the black hole can influence the dynamics of the galaxy, regulating star formation and even driving outflows of gas and energy that shape the surrounding environment. The disk of a spiral galaxy is where most of the galaxy's visible stars, gas, and dust are located. It is within the disk that the spiral arms are found, and it is also where the majority of the galaxy's star formation occurs. The disk is typically thin, with stars arranged in a flattened, rotating structure. The rotation of the disk is a crucial aspect of the galaxy's overall dynamics, and it is what gives spiral galaxies their characteristic shape. The stars in the disk move in near-circular orbits, with the speed of rotation decreasing with distance from the galactic center. This rotational motion is a result of the galaxy's gravitational forces, with the stars being held in place by the gravity of the galaxy's dark matter halo. Over time, the disk of a spiral galaxy can undergo significant changes. Star formation within the disk is influenced by the supply of gas and dust, which can be affected by both internal and external factors. For example, interactions with nearby galaxies can cause gas to be funneled into the disk, triggering a burst of star formation. Conversely, the loss of gas through supernova explosions, stellar winds, and feedback from the central black hole can slow down or even halt star formation. The balance between the creation and destruction of stars in the disk plays a crucial role in shaping the galaxy's overall evolution. One of the most exciting areas of research in galactic evolution is the role of mergers and interactions between galaxies. As mentioned earlier, galaxy mergers are a common phenomenon in the universe, and they have a profound effect on the shape and structure of galaxies. When two galaxies collide, the gas and stars within each galaxy are redistributed, often leading to the formation of new structures. In the case of spiral galaxies, mergers can lead to the disruption of the spiral arms, the formation of a central bulge, and the eventual transformation of the galaxy into an elliptical galaxy. These mergers can also trigger bursts of star formation, as the gas in the galaxies is compressed during the collision. The effects of galaxy mergers are not limited to the immediate aftermath of the collision. Over time, the galaxies involved in a merger can continue to evolve, with the newly formed elliptical galaxy gradually settling into a more stable configuration. The process of galactic cannibalism, in which one galaxy absorbs another, can also lead to the growth of supermassive black holes in the centers of galaxies. These black holes can continue to grow over time, becoming a dominant feature of the galaxy. While mergers are a key factor in the evolution of spiral galaxies, they are not the only external force that can shape a galaxy. The environment in which a galaxy resides also plays a significant role in its development. Galaxies are not isolated objects but are part of larger cosmic structures, such as galaxy clusters and superclusters. These larger structures can have a profound impact on the evolution of galaxies, particularly through processes like ram pressure stripping and tidal interactions. Ram pressure stripping occurs when a galaxy moves through the hot gas that exists between galaxies in a cluster. As the galaxy moves through this gas, the pressure from the surrounding medium can strip away the galaxy's outer layers of gas, slowing down star formation and potentially leading to the eventual quenching of the galaxy. Tidal interactions, on the other hand, occur when two galaxies pass close to one another, leading to the distortion of their shapes and the exchange of material. These interactions can cause the spiral arms of a galaxy to become distorted or even completely disrupted, leading to changes in the galaxy's overall structure. The study of spiral galaxies is a constantly evolving field, with new discoveries being made on a regular basis. As our understanding of the universe deepens, we continue to learn more about the complex processes that govern the formation, evolution, and eventual fate of spiral galaxies. From the role of dark matter and halos to the effects of mergers and interactions, the evolution of these galaxies is a testament to the dynamic nature of the cosmos. The future of spiral galaxies, particularly our own Milky Way, is a subject of great interest and speculation. The upcoming collision with the Andromeda Galaxy, while billions of years away, will have a profound impact on the structure and evolution of both galaxies. As the two galaxies merge, their spiral arms will be disrupted, and the resulting structure will likely be an elliptical galaxy. However, the exact outcome of this collision is still uncertain, and much depends on the nature of the interaction and the processes that occur during the merger. The evolution of spiral galaxies is a tale of constant change, driven by both internal processes and external forces. Whether through the formation of new stars in the spiral arms, the growth of supermassive black holes in the center, or the disruption caused by mergers and interactions, spiral galaxies continue to evolve and transform over vast periods of time. The study of these galaxies not only helps us understand the forces that shape the universe but also provides us with a glimpse into the future of our own galaxy. As we continue to delve into the intricacies of spiral galaxies, it's essential to consider how the discovery of these objects has expanded our understanding of the universe. The first spiral galaxy to be observed was the Andromeda Galaxy, which has long been a subject of fascination for astronomers. The recognition that our galaxy, the Milky Way, is also a spiral galaxy marked a turning point in the study of cosmology, allowing scientists to draw connections between the structure of our galaxy and other galaxies in the universe. One of the most important questions that arise when we think about the formation and evolution of spiral galaxies is how and when they began to take shape. The formation of galaxies, including spiral galaxies, is believed to have occurred during the early stages of the universe. Shortly after the Big Bang, a vast amount of gas and dust existed in the universe, and the formation of galaxies was driven by the gravitational collapse of these materials. Over time, the gas condensed into the first generation of stars, and the interactions between these stars led to the formation of the characteristic structures we observe in galaxies today. The early stages of galaxy formation were likely chaotic and tumultuous. As gas and dust began to collapse under gravity, it formed clumps of matter that eventually gave rise to stars. The gravitational forces exerted by these stars caused the surrounding gas to rotate, which, in turn, set the stage for the formation of a galaxy's disk. Over time, this rotating disk began to flatten, and the galaxy's spiral arms began to take shape. The precise mechanisms behind the formation of these arms are still an area of active research, but it is generally believed that they form through density waves, regions of high gravitational pull that cause the gas and stars to bunch together, creating the spiral patterns. The early universe was a vastly different place than what we observe today. There was much more gas available for star formation, and galaxies were actively forming stars at a much faster rate than they do now. Over time, As galaxies aged and expended much of their available gas through star formation, the rate of new star creation slowed down. This shift had a profound effect on the appearance and structure of galaxies, as older, less active galaxies began to take on more stable, mature forms. The star formation in spiral galaxies, while still ongoing, gradually slowed, and many of these galaxies reached a state of equilibrium where the rate of new stars being born was balanced by the rate at which older stars died. Spiral galaxies are also characterized by the presence of a significant amount of dark matter. Dark matter is an invisible form of matter that does not emit light or other forms of electromagnetic radiation, but its presence is inferred from its gravitational effects on visible matter. The role of dark matter in the formation and evolution of spiral galaxies is a topic of ongoing research. It is believed that dark matter halos surround galaxies, providing the additional gravitational pull necessary to keep the galaxies intact. These dark matter halos play a critical role in the dynamics of spiral galaxies, helping to stabilize the rotation of the galaxy and prevent it from falling apart due to its own rotation. One of the most fascinating aspects of spiral galaxies is their incredible diversity. While many spiral galaxies share certain common features, such as spiral arms and central bulges, each galaxy is unique in its own right. For instance, some spiral galaxies have tightly wound spiral arms, while others have arms that appear more loosely wound. The number of spiral arms can also vary, with some galaxies exhibiting 2 arms, while others have 4 or more. The size of the central bulge and the thickness of the galactic disk can also differ greatly from one galaxy to another. Another factor that contributes to the diversity of spiral galaxies is their environment. Galaxies that reside in dense clusters, where they are in close proximity to other galaxies, often exhibit different characteristics than those in more isolated regions. In crowded environments, interactions between galaxies are more common, and these interactions can lead to changes in the structure and dynamics of a spiral galaxy. For example, a spiral galaxy that experiences a close encounter with another galaxy may have its spiral arms disrupted, or it may undergo a transformation into a more elliptical shape. The effects of galaxy mergers, such as the ones that occur in galaxy clusters, can also lead to the growth of supermassive black holes in the centers of galaxies, further altering their structure. Despite the diversity of spiral galaxies, there are also certain characteristics that are common to most of them. For example, the spiral arms of most galaxies contain significant amounts of gas and dust, as well as young, hot stars. These stars are often found in regions of the arms where star formation is actively occurring. The central bulge, on the other hand, is usually populated by older stars that have been in the galaxy for a longer period of time. This contrast between the young, bright stars of the arms and the older, dimmer stars of the bulge is one of the key features that distinguish spiral galaxies from other types of galaxies, such as elliptical galaxies, which are composed primarily of older stars. Understanding the evolution of spiral galaxies also requires considering the processes that occur within them. For example, the presence of supernovae, which are the explosive deaths of massive stars, plays an important role in shaping the galaxy's evolution. Supernovae release vast amounts of energy, and can trigger the formation of new stars by compressing nearby gas clouds. Additionally, the energy and matter expelled by supernovae can create large-scale shock waves that affect the surrounding region, pushing gas and dust into new regions of the galaxy. These shock waves can trigger further star formation and lead to the growth of the galaxy. Another key process in the evolution of spiral galaxies is the formation and growth of supermassive black holes. These black holes, which are thought to reside at the centers of most large galaxies, can have a profound impact on their host galaxies. As matter falls into the black hole, it releases enormous amounts of energy, which can heat up the surrounding gas and dust. This heating can inhibit the formation of new stars, leading to a slowdown in star formation and causing the galaxy to evolve into a more quiescent state. The growth of the black hole can also influence the galaxy's structure by altering the dynamics of the stars and gas in the central region. As we move forward, the study of spiral galaxies continues to evolve. New technologies, such as advanced telescopes and space observatories, are allowing astronomers to peer deeper into space than ever before, revealing new details about the formation and evolution of these galaxies. Through these observations, we are learning more about the processes that shape galaxies, from the formation of their spiral arms to the growth of their central bulges and supermassive black holes. The ongoing exploration of spiral galaxies also raises new questions about the ultimate fate of these galaxies. While many spiral galaxies, including the Milky Way, are expected to continue evolving for billions of years, the eventual collision between the Milky Way and the Andromeda Galaxy will dramatically alter the structure of both galaxies. As these two galaxies merge, their spiral arms will be disrupted, and the resulting galaxy will likely take on a more elliptical shape. This collision will not only change the appearance of the galaxies, but will also trigger a new phase of star formation and potentially lead to the growth of a larger supermassive black hole at the center of the newly merged galaxy. The evolution of spiral galaxies is a complex and ongoing process that is shaped by a combination of internal forces and external interactions. From the formation of their spiral arms and bulges to the role of dark matter and black holes, spiral galaxies are dynamic objects that continue to evolve over vast periods of time. As we continue to explore these galaxies and learn more about their evolution, we gain valuable insights into the broader workings of the universe and the forces that govern the formation and evolution of galaxies. As we continue to examine the evolution of spiral galaxies, it's important to highlight the impact that galaxy interactions and mergers have on their development. While the majority of spiral galaxies are relatively isolated or only interact slightly with their neighbors, galaxy collisions are common in the broader universe, and they play a pivotal role in shaping the evolution of galaxies. These interactions can lead to significant changes in a galaxy's structure, star formation, and overall appearance. When two galaxies collide, the result is often a dramatic transformation of both galaxies. In the case of spiral galaxies, the collision can cause their beautiful, symmetric spiral arms to become distorted or completely destroyed. The intense gravitational interactions between the two galaxies can cause the gas and dust in the galaxies to compress, triggering a burst of star formation, known as a starburst. However, this intense activity is often short-lived, as the gas and dust used in star formation becomes depleted, leaving behind a more stable and evolved galaxy. During these collisions, the central regions of both galaxies often experience intense gravitational forces, which can lead to the formation of a new supermassive black hole at the center of the merged system. The combination of these black holes can result in an incredibly powerful galactic core that emits vast amounts of energy, altering the galaxy's future evolution. This process of black hole merger is still an area of active research, as scientists seek to understand the role these mergers play in the broader cosmic structure. In the case of the Milky Way, which is on a collision course with the Andromeda Galaxy, the merger will have profound effects not only on the structure of both galaxies, but also on the fate of the stars within them. It's believed that most stars within the galaxies will avoid direct collisions due to the vast distances between them, but the gravitational forces will rearrange the stars and potentially trigger the formation of new stars in previously inactive regions. The result of the merger between the Milky Way and Andromeda will be a larger, more elliptical galaxy, and the spiral structure that defines both galaxies will be lost over time. On a smaller scale, interactions between spiral galaxies and their satellite galaxies or nearby smaller galaxies can also lead to significant changes. These smaller galaxies may be pulled into the larger spiral galaxy, disrupting the delicate balance of the spiral arms and contributing additional gas and dust that can spur further star formation. Over time, the smaller galaxy may be completely absorbed into the larger spiral galaxy, further altering its structure. Another interesting aspect of spiral galaxy evolution is the potential for them to transition into different types of galaxies. While spiral galaxies are generally stable in their spiral structure, some can evolve into lenticular galaxies. These galaxies have a disc-like structure but lack the distinct spiral arms, and they appear to be a transition state between spirals and elliptical galaxies. This transition is thought to occur when the galaxy's gas supply is depleted or when interactions with other galaxies strip away the outer layers of the spiral arms. The gas loss reduces the galaxy's ability to form new stars, causing it to lose its characteristic spiral shape. As spiral galaxies age, their central bulges grow and evolve, often taking on a more dominant role in the overall structure of the galaxy. The central bulge consists of older stars and is thought to have formed early in the galaxy's life. These bulges are often composed of a mix of stars that range in age, from relatively young stars to ancient ones. Over time, the stellar population in the bulge may continue to evolve, with new stars forming in the outer regions, but the central regions of the bulge may remain relatively static in terms of star formation. This suggests that the processes occurring in the center of a spiral galaxy are crucial in determining its long-term evolution. Furthermore, recent studies have shown that spiral galaxies may experience a gradual transformation into passive galaxies as they use up their gas reservoirs. As star formation slows down, the galaxy becomes less active, and the spiral arms begin to fade, leaving behind a less dynamic and more featureless disk. This process can take billions of years, and it results in a galaxy that looks similar to an elliptical galaxy in terms of its structure, even though its star formation history is different. One critical element in understanding the fate of spiral galaxies is the role of dark energy. Dark energy is a mysterious force that is driving the accelerated expansion of the universe, and its effects are likely to become more pronounced over time. As galaxies move further apart due to the expansion of the universe, the interactions between galaxies will become less frequent. This could lead to a decrease in galaxy mergers and interactions, allowing individual galaxies to evolve more slowly. For spiral galaxies, this means that the processes of gas depletion, black hole growth, and aging will continue, but they may do so at a slower pace than in the past. The study of spiral galaxies and their evolution has been greatly enhanced by advancements in technology, particularly with the launch of space-based telescopes. Instruments like the Hubble Space Telescope and the recently launched James Webb Space Telescope have provided astronomers with unprecedented views of distant galaxies, allowing them to peer into the heart of spiral galaxies and observe their intricate details. These telescopes have enabled scientists to study the interactions between galaxies, the formation of stars, and the behavior of supermassive black holes in ways that were once unimaginable. The data gathered from these observations is providing critical insights into the past, present, and future of spiral galaxies. By studying galaxies at various stages of their evolution, astronomers can better understand how galaxies form, evolve, and interact with their environment. The wealth of information gathered from spiral galaxies allows scientists to piece together a more complete picture of the universe's history and the complex processes that drive the formation of galaxies. Additionally, the study of spiral galaxies offers valuable clues about the broader structure of the universe. By analyzing the distribution of spiral galaxies across different regions of the universe, astronomers can map out the large-scale structure of the cosmos. This helps scientists understand the cosmic web, a vast network of galaxies and galaxy clusters connected by vast, empty regions known as cosmic voids. Understanding the distribution of spiral galaxies and their role within this web is key to unraveling the mysteries of cosmic evolution. As we look to the future, the ongoing exploration of spiral galaxies promises to answer some of the most fundamental questions about the universe. How did galaxies form, and what processes have shaped their evolution over billions of years? What will happen to the Milky Way and other spiral galaxies as they continue to age? Will the merger between the Milky Way and Andromeda lead to the creation of a new type of galaxy? Or will it be just one chapter in the ongoing story of galaxy evolution? Spiral galaxies are not only some of the most beautiful and recognizable objects in the universe but also some of the most complex. Their evolution is shaped by a combination of internal and external forces, including star formation, supermassive black holes, dark matter, and galaxy interactions. As we continue to study these fascinating galaxies, we uncover more about the nature of the universe itself and the dynamic processes that have shaped it over billions of years. The evolution of spiral galaxies is not just about the galaxies themselves, but about the entire cosmos and the forces that govern its development. As we continue to unravel the mysteries of spiral galaxies, it's important to acknowledge that the study of these cosmic structures is not just a matter of understanding their past and present, but also predicting their future. The way spiral galaxies evolve is a reflection of the broader cosmic environment, and it also reveals much about the fate of the universe itself. As we gaze into the vast expanse of space, each spiral galaxy tells a story about the forces at work within it, and the intricate processes that shape the universe over time. One of the critical elements in predicting the future of spiral galaxies is the ongoing process of stellar evolution. Stars within a spiral galaxy do not live forever. The majority of stars follow a predictable life cycle, from their formation in the galaxy's spiral arms to their eventual death, which can take the form of a supernova explosion, a planetary nebula, or the quiet cooling of a white dwarf. The death of stars has profound effects on the galaxy. When stars explode in supernovae, they release vast amounts of energy, as well as heavy elements, into the surrounding interstellar medium. These materials enrich the galaxy, contributing to the formation of new stars and planets. The cycle of stellar birth and death is an ongoing process that fuels the galaxy's evolution. However, the death of stars also contributes to the depletion of a galaxy's gas reserves. As stars age and die, the gas used to form them becomes part of the galaxy's overall composition, but it is no longer available for new star formation. Over time, this depletion of gas leads to a decline in the galaxy's ability to form new stars, a process known as galactic quenching. The consequences of galactic quenching are profound. As new stars are no longer formed, the galaxy becomes increasingly populated with older, less active stars, and its once vibrant spiral arms fade. The galaxy transitions from being a dynamic, star-forming system into a more passive, older structure. This transition is one of the key signs that a spiral galaxy has entered the later stages of its life cycle. Interestingly, the process of galactic quenching is not always uniform across a galaxy. While the outer regions of the galaxy may continue to experience star formation for a time, the central bulge often becomes the most dominant feature as gas is depleted. The central bulge of a spiral galaxy contains older stars, and in many cases, it is home to a supermassive black hole. As star formation in the outer regions slows down, the central bulge becomes more prominent, and the galaxy itself may evolve into a lenticular galaxy, which is characterized by a smooth, featureless disk without the distinct spiral arms. In addition to the natural processes that contribute to a galaxy's evolution, the role of dark matter cannot be understated. Dark matter is an invisible, mysterious substance that makes up a significant portion of the universe's mass. Although it does not emit light or interact with regular matter in ways that we can directly detect, its gravitational effects are undeniable. Dark matter exerts a strong influence on the overall structure of galaxies, and spiral galaxies are no exception. In fact, the spiral structure of a galaxy is thought to be partly the result of the gravitational influence of dark matter. The distribution of dark matter within a galaxy helps to maintain the galaxy's shape, keeping the spiral arms intact and preventing them from unraveling. As we look to the distant future of spiral galaxies, it is likely that many will face the same fate as the Milky Way. In about 4 billion years, the Milky Way will collide with the Andromeda Galaxy, and this merger will have profound consequences for both galaxies. The collision will result in the disruption of their spiral arms, and the two galaxies will eventually combine to form a larger, elliptical galaxy. This merger is expected to be a slow process, taking place over billions of years, and it will completely transform the structure of both galaxies. The end result will be a massive, elliptical galaxy that no longer retains the familiar spiral arms of its predecessors. However, not all spiral galaxies are headed toward mergers. Some galaxies may evolve in isolation, gradually losing their star-forming potential as their gas reservoirs are depleted. These galaxies may slowly fade into passive systems, their once bright spiral arms becoming more and more diffuse over time. This gradual process of fading is a reminder that the universe is in a constant state of flux, with galaxies evolving in response to both internal and external forces. As galaxies continue to evolve, they will contribute to the ever-changing cosmic landscape. The study of spiral galaxies is not only about understanding their evolution, but also about gaining insight into the broader processes that govern the universe. By studying how these galaxies form, evolve, and interact with their environments, astronomers can learn about the fundamental forces that shape the cosmos. The way galaxies evolve over time is tied to the fate of the universe itself, as galaxies are the building blocks of the cosmic web. Understanding the life cycle of galaxies helps scientists make predictions about the future of the universe, including the role of dark energy, the expansion of the cosmos, and the ultimate fate of the galaxies that populate it. As technology advances, astronomers are able to study spiral galaxies in increasingly greater detail. The development of next-generation telescopes, such as the James Webb Space Telescope, will provide even more detailed observations of galaxies in different stages of their evolution. With these new tools, scientists will be able to peer deeper into the cosmos than ever before, observing galaxies that formed in the early universe and exploring their evolution over billions of years. These observations will offer new insights into the processes that drive galaxy formation and evolution, as well as the role of dark matter, dark energy, and other mysterious forces that shape the universe. The continued exploration of spiral galaxies promises to reveal more about the nature of the universe than we could have ever imagined. The more we learn about these stunningly complex and beautiful objects, the closer we come to understanding the larger cosmic picture. Spiral galaxies are not just islands of stars in the vastness of space. They are key players in the ongoing story of the universe's evolution. Each galaxy, with its intricate spiral arms and central bulge, tells a story about the forces at work in the cosmos and offers clues about the past, present, and future of the universe itself. As we look to the future of galactic exploration, one thing is certain: the evolution of spiral galaxies will continue to be a central focus of scientific inquiry. These galaxies offer a window into the broader processes that shape the universe, and their study will help us answer some of the most profound questions about the nature of space, time, and the cosmos. The more we learn about spiral galaxies and their evolution, the more we realize that we are part of a much larger story, one that spans billions of years and stretches across the entire universe. The evolution of spiral galaxies is not just about the fate of individual galaxies, but about the story of the universe itself. It is a tale of growth, change, and transformation, driven by the complex interplay of gravitational forces, dark matter, star formation, and cosmic interactions. As we continue to explore the mysteries of spiral galaxies, we are not just uncovering the secrets of these beautiful cosmic structures, but also learning about the forces that govern the universe on the grandest scale. The study of spiral galaxies continues to be one of the most fascinating fields in modern astronomy. As we delve deeper into their evolution, it's crucial to understand the complex forces and processes that drive their transformations. Every spiral galaxy we observe today has gone through an incredible journey, influenced by a myriad of factors ranging from stellar formation to galactic mergers. These processes are not just isolated to individual galaxies but are reflective of the larger, ever-changing universe. As scientists gather more data and refine our understanding, we are not just learning about the galaxies themselves but gaining profound insights into the history and future of the cosmos. The impact of galactic mergers is one of the most captivating aspects of galaxy evolution. Mergers between galaxies can profoundly alter their structure and evolution. When two spiral galaxies collide, their spiral arms often become distorted, and their stars interact in ways that can lead to the formation of new star systems or, conversely, the disruption of existing ones. The process can take billions of years, but the result is often the formation of an elliptical galaxy, one that lacks the characteristic spiral arms. These mergers serve as a natural part of the life cycle of galaxies, highlighting the dynamic nature of the universe. The Milky Way, our very own spiral galaxy, is on a collision course with the Andromeda Galaxy. This impending collision, predicted to occur in about 4 billion years, will likely lead to the formation of a new elliptical galaxy. The Milky Way and Andromeda are both massive galaxies, and when they merge, the process will involve the slow dance of millions of stars as they pass through each other, with their spiral structures collapsing and reforming over time. Although individual stars are unlikely to collide due to the vast distances between them, the gravitational forces between the two galaxies will be enough to drastically reshape their structures. This event will be a defining moment in the evolution of our galaxy, though it is still many billions of years away. The merging of galaxies is not a rare phenomenon but rather a common aspect of galactic evolution. Over time, smaller galaxies will continue to collide and merge with larger ones, contributing to the growth of massive galaxies. These interactions not only alter the galaxies involved but also have significant implications for their surrounding environments. The merging process can trigger intense periods of star formation, known as starbursts, where large numbers of new stars are born from the gas and dust stirred up during the collision. These starbursts can result in the creation of new stars at an accelerated rate, temporarily reviving a galaxy's star-forming capabilities even as it loses its distinct spiral structure. In addition to these violent collisions, spiral galaxies can also experience a more gradual transformation over time. As the galaxy's gas supply is depleted and star formation slows, the galaxy may begin to lose its spiral arms. This gradual fading can result from a combination of factors, including the cessation of star formation, the depletion of gas, and the influence of the galaxy's central black hole. The central bulge of the galaxy, which contains a high concentration of older stars, may begin to dominate the galaxy's appearance. Over time, this transformation can turn a spiral galaxy into a lenticular galaxy, which is essentially a disc-shaped galaxy without distinct spiral arms. While the galaxy still retains some of its structural elements, it loses the dynamic, active characteristics of a spiral galaxy. Understanding the mechanics of these transformations requires a deep dive into the role of the central black hole. Nearly every spiral galaxy, including the Milky Way, harbors a supermassive black hole at its center. These black holes are not just passive objects, they are active participants in the evolution of their host galaxies. As gas falls into the black hole, it can release tremendous amounts of energy in the form of radiation and jets. This energy can have a significant impact on the galaxy, potentially heating up gas and preventing it from cooling and collapsing into new stars. The active galactic nucleus, or AGN, formed by the central black hole's influence, plays a key role in regulating star formation and in the evolution of the galaxy as a whole. But while these processes work to deplete the gas supply and slow star formation, the galaxy itself may not be entirely passive. In many cases, spiral galaxies are still interacting with their environment, through phenomena such as accretion and mergers. Even when a galaxy is no longer forming stars at a high rate, it may continue to evolve by absorbing smaller galaxies or gas clouds. This constant interaction with its surroundings ensures that even as spiral galaxies age, they remain dynamic systems capable of transformation. Dark matter remains one of the most mysterious yet crucial components in the evolution of spiral galaxies. The invisible presence of dark matter around galaxies is what helps maintain their structure. Dark matter doesn't emit light, making it incredibly difficult to detect directly. However, its gravitational pull is substantial, and it has been detected through its influence on the rotation of galaxies. Without dark matter, the outer regions of spiral galaxies would rotate much more slowly than they do. The presence of dark matter ensures that the stars in the outer arms of a galaxy stay in place, preventing the galaxy from flying apart. Dark matter acts as the invisible glue that holds galaxies together, playing an essential role in their stability and evolution. As we continue to investigate spiral galaxies, the role of dark energy is becoming an increasingly important part of the equation. Dark energy, the mysterious force thought to be driving the accelerated expansion of the universe, may also influence the way galaxies evolve. While its direct effect on individual galaxies is not yet fully understood, dark energy could be responsible for altering the way galaxies interact with each other over cosmic timescales. As the universe continues to expand, dark energy may influence the interactions between galaxies, including their mergers and the ultimate fate of the cosmic structures we observe. The technological advances in astronomy are revolutionizing our understanding of spiral galaxies. The advent of space-based telescopes like the Hubble Space Telescope, the Chandra X-ray Observatory, and the James Webb Space Telescope has allowed scientists to observe galaxies with unprecedented clarity. These telescopes enable us to peer deeper into the cosmos, revealing galaxies in various stages of their evolution. They allow astronomers to observe the intricate details of spiral galaxies, from the structure of their arms to the behavior of their central black holes. As new data is collected, our understanding of spiral galaxies continues to evolve, providing a clearer picture of how they form, grow, and ultimately transform over billions of years. In the distant future, our understanding of spiral galaxies may be enhanced even further by the development of new observational techniques and more powerful telescopes. As we continue to study these incredible cosmic structures, we will uncover more secrets about the universe's past, present, and future. Spiral galaxies may seem like distant, static objects in the night sky, but they are dynamic, evolving systems that hold clues to some of the most profound questions in cosmology. The evolution of spiral galaxies is a story of growth, transformation, and eventual decline. Through stellar birth and death, galactic mergers, and the interplay of forces like dark matter and dark energy, these galaxies evolve in ways that reflect the larger processes shaping the universe. By studying their evolution, we gain insight into the workings of the cosmos, from the smallest stars to the largest structures in the universe. As we look to the future, the evolution of spiral galaxies will continue to be a central part of our understanding of the universe's grand narrative, shedding light on the forces that shape everything from individual galaxies to the universe itself. The ongoing evolution of spiral galaxies is a testament to the dynamic and constantly changing nature of the universe. As we continue to peer into the depths of space and gather more data, we are beginning to see the intricate details of how these galaxies evolve. One of the key aspects of this process is the interplay between the galaxy's gas and its stars. Gas is the lifeblood of a galaxy, fueling star formation and acting as a medium for the galaxy's growth. However, over time, galaxies exhaust their gas supply, which leads to the cessation of star formation and marks the beginning of a gradual transition in their evolution. The process through which a spiral galaxy depletes its gas is a complex one. Initially, when gas is abundant, a galaxy experiences periods of vigorous star formation, which is what gives spiral galaxies their characteristic appearance. The gas in the galaxy's disk collapses under gravity, forming clusters of young, hot stars that shine brightly and illuminate the surrounding gas. These stars, particularly the most massive ones, can influence their environment by emitting intense radiation and winds. This feedback process can either regulate or trigger further star formation, depending on the balance of forces within the galaxy. However, as time progresses, the gas supply starts to dwindle. Some of it is used up in the formation of stars, while other portions are expelled from the galaxy due to processes like supernova explosions, which can blow gas out of the galaxy's disk. This is particularly evident in galaxies that are experiencing active star formation. The loss of gas makes it increasingly difficult for a galaxy to maintain its spiral structure. Over billions of years, the once vibrant arms of the spiral galaxy may begin to fade, and the galaxy could lose its ability to produce new stars. The evolution of spiral galaxies is also influenced by the movement of gas within the galaxy. In many cases, the gas flows inward towards the center of the galaxy, where it can be pulled into the supermassive black hole at the galaxy's core. As this gas accretes onto the black hole, it can trigger the formation of an active galactic nucleus, AGN, a highly energetic region at the center of the galaxy. AGNs can emit large amounts of radiation, which can have profound effects on the surrounding galaxy. In some cases, the intense radiation from the AGN can blow away gas, preventing further star formation and effectively halting the galaxy's evolution. This feedback process is an important factor in determining the fate of spiral galaxies, as it can regulate both the rate of star formation and the amount of available gas. While the depletion of gas is a significant factor in the evolution of spiral galaxies, another key aspect of their transformation is the impact of mergers and interactions with other galaxies. These galactic encounters can play a crucial role in shaping the structure and dynamics of spiral galaxies. When two galaxies collide, their gravitational forces can cause massive disturbances in the gas and stars of both galaxies. In some cases, the spiral arms of the galaxies can become distorted or even completely disrupted. The merger process can trigger intense bursts of star formation, known as starbursts, where large numbers of stars are born in a short period of time. However, this process is not without its consequences. The disruption of a galaxy's spiral structure can lead to the formation of an elliptical galaxy, which is characterized by a smooth, featureless appearance, lacking the distinct arms that define spiral galaxies. Even after a merger, the evolution of the resulting galaxy continues. In the case of two spiral galaxies merging, the new galaxy may eventually settle into a more elliptical shape, although the remnants of the spiral arms may still be visible in the form of faint structures or irregularities. This process of galactic transformation is gradual and can take billions of years to complete, but it serves as a reminder that even the most well-known galaxies, like the Milky Way, are not static. They are constantly evolving, reshaping themselves in response to both internal and external forces. One of the most fascinating aspects of the evolution of spiral galaxies is their ability to retain their spiral structure for such long periods of time. While galactic mergers can disrupt a galaxy's spiral arms, many spiral galaxies, including the Milky Way, have retained their distinctive structure for billions of years. This resilience is due in part to the stability of the galaxy's overall structure. The gravitational forces within a spiral galaxy are finely tuned, with the outer stars and gas in the spiral arms moving in a way that preserves the integrity of the galaxy. This delicate balance between the forces of gravity, rotation, and gas dynamics allows spiral galaxies to maintain their iconic spiral structure for such long timescales. The preservation of spiral structure is also influenced by the presence of dark matter. Dark matter is an invisible substance that makes up a significant portion of the mass of a galaxy. While it cannot be directly observed, its presence can be inferred through its gravitational effects on visible matter. Dark matter plays a crucial role in the stability of spiral galaxies. It forms a halo around the galaxy, providing the necessary gravitational pull to prevent the outer stars and gas from flying off into space. Without dark matter, the spiral arms of a galaxy would be much less stable, and the galaxy could eventually lose its spiral structure. The role of dark matter in galactic evolution is still an area of active research, but it is clear that it is an essential component in the formation and long-term survival of spiral galaxies. As we look to the future, the continued study of spiral galaxies promises to yield even more insights into the processes that shape the universe. With the development of more advanced telescopes and observational techniques, we will be able to observe galaxies in greater detail than ever before. This will allow scientists to better understand the complex interplay between gas, stars, and dark matter, and how these factors contribute to the evolution of galaxies over cosmic timescales. The study of spiral galaxies is not just about understanding the galaxies themselves, but also about unraveling the larger mysteries of the universe. One of the most exciting areas of research in this field is the role of spiral galaxies in the formation of supermassive black holes. Nearly every large galaxy, including the Milky Way, harbors a supermassive black hole at its center. These black holes are millions or even billions of times more massive than our Sun, and their formation is still not fully understood. It is believed that supermassive black holes may play a significant role in the evolution of galaxies, particularly in regulating the rate of star formation and the growth of the galaxy itself. The exact mechanism through which supermassive black holes influence galaxy evolution is still a subject of intense study, but it is clear that they are integral to the story of spiral galaxies. The future of spiral galaxies is intrinsically tied to the ongoing expansion of the universe. As the universe continues to grow, galaxies are becoming more and more distant from one another. This expansion, driven by the mysterious force of dark energy, may eventually lead to the isolation of individual galaxies. As galaxies drift further apart, the chances of future galactic mergers decrease. This could signal the end of the era of galactic collisions, marking a new phase in the evolution of the cosmos. While the distant future may seem far off, the current era of galactic interactions and mergers is one of the most dynamic periods in the history of the universe. Ultimately, the evolution of spiral galaxies offers a fascinating glimpse into the life cycle of galaxies and the forces that shape the universe. From their formation in the early universe to their eventual transformation into elliptical galaxies, spiral galaxies are a testament to the incredible processes that govern the cosmos. Each spiral galaxy is a living, breathing entity, constantly evolving and interacting with the universe around it. As we continue to explore the mysteries of the universe, the study of spiral galaxies will undoubtedly remain one of the most intriguing and important areas of research in cosmology. As we continue to investigate the evolution of spiral galaxies, it's important to consider the role that the interstellar medium, ISM, plays in their transformation. The ISM consists of the gas, dust, and cosmic rays that exist between stars within a galaxy. This material is crucial not only for the formation of stars but also for shaping the galaxy's overall structure. In spiral galaxies, the ISM is often distributed in a disk-like structure, which is why we see these galaxies form well-defined spiral arms. The density of gas within the disk of a spiral galaxy determines the rate of star formation. Regions of the ISM with higher densities are where new stars are born. These regions often appear as bright blue patches in images of spiral galaxies because young, hot stars are shining brightly. These young stars are often surrounded by molecular clouds of gas and dust, and their intense radiation can cause the surrounding gas to collapse and form even more stars. However, as star formation progresses, it generates strong feedback that impacts the ISM. The most massive stars, particularly those at the end of their life cycle, explode as supernovae, releasing vast amounts of energy into the surrounding gas. This feedback can cause the gas to be heated, accelerated, and even expelled from the galaxy, potentially leaving behind areas with very little gas to form new stars. Over time, this depletes the galaxy's supply of star-forming material, and the rate of new stars being created slows down. When this happens, the galaxy's spiral structure starts to fade, and the once vibrant arms begin to blur into a more diffuse pattern. Another aspect of the ISM that plays a role in galaxy evolution is the magnetic field. Spiral galaxies typically have large-scale magnetic fields that thread through the gas in the disk. These magnetic fields can have a significant influence on the movement of the gas, affecting both star formation and the dynamics of the galaxy as a whole. Some scientists believe that the magnetic field could even help to maintain the spiral structure of the galaxy, acting as a stabilizing force that prevents the gas from dispersing too rapidly. In the broader context, the study of spiral galaxy evolution provides important clues about the life cycle of galaxies. While spiral galaxies are commonly thought to be in a relatively youthful phase of their existence, they too will eventually evolve into different forms. After billions of years, the galaxy may undergo transformations due to the depletion of its gas or through interactions with other galaxies. When the gas supply is exhausted, and star formation slows down, the galaxy will enter what astronomers refer to as a quiescent phase. During this time, the galaxy may become a red-ended elliptical galaxy, characterized by a lack of star formation and a more uniform, spherical shape. This transition occurs slowly, over the course of billions of years, and provides an important window into the long-term evolution of galaxies. Even as spiral galaxies evolve and change, their fascinating structures continue to captivate astronomers and cosmologists. The central bulge of a spiral galaxy, for instance, contains a dense concentration of older stars and can provide vital information about the history of the galaxy. Bulges are thought to form early in a galaxy's history, during the initial collapse of gas and dust. Over time, these bulges evolve and can affect the overall dynamics of the galaxy. The relationship between the central bulge and the disk is key to understanding how a spiral galaxy evolves, and it helps scientists explore the processes that influence galactic growth and transformation. The interplay between the central bulge and the spiral arms is also a subject of ongoing research. The spiral arms of a galaxy are not solid structures but rather waves of density that travel through the galaxy's disk. These density waves are thought to be caused by the gravitational interaction between stars, gas, and dark matter within the galaxy. As these waves move through the disk, they compress the gas in their wake, triggering star formation. This process is essential to maintaining the spiral structure of the galaxy over time. Interestingly, the spiral arms are not permanent features of a galaxy. In fact, over time, the arms can change shape or fade away entirely. Some theories suggest that the arms might only be transient phenomena that arise during certain stages of a galaxy's evolution, influenced by factors such as the galaxy's rotation rate, the distribution of gas, or the presence of nearby galaxies. Understanding how and why these arms evolve is a critical piece of the puzzle when it comes to studying galaxy formation. Spiral galaxies are also important in the study of dark matter. The presence of dark matter is inferred from its gravitational effects on visible matter, and it plays a crucial role in maintaining the stability of galaxies. While we cannot observe dark matter directly, we know it makes up a large part of the mass of spiral galaxies. The dark matter halo surrounding a spiral galaxy is believed to exert a gravitational pull that helps to keep the galaxy intact, preventing the stars in the outer regions from flying off into space due to the galaxy's rotation. The interaction between dark matter and the visible matter in a spiral galaxy is a fascinating area of research. Some scientists believe that dark matter could help to stabilize the spiral arms, while others suggest that dark matter's influence might extend to the central bulge as well. As we continue to study dark matter and its effects on galaxies, we will likely gain new insights into the fundamental nature of both galaxies and the universe as a whole. As spiral galaxies age, their star formation rate gradually decreases. While galaxies like the Milky Way have been forming stars for billions of years, the rate at which they create new stars will eventually slow down. The gas that fuels star formation becomes increasingly scarce, and the remaining gas may be locked away in cold molecular clouds or driven out of the galaxy by energetic feedback processes. When star formation essentially stops, the galaxy enters a phase known as passive evolution. During this time, the galaxy will continue to evolve, but without the formation of new stars, the galaxy's appearance will change dramatically. The once vibrant spiral arms will become less defined, and the galaxy will begin to fade into a more featureless elliptical shape. The fate of spiral galaxies is largely determined by their environment. Galaxies that are part of a large cluster are more likely to undergo interactions and mergers, which can accelerate their transition into elliptical galaxies. In contrast, isolated spiral galaxies in the vast voids of the universe are more likely to retain their spiral structure for longer periods of time. The future of individual galaxies depends not only on the gas within them but also on their interactions with neighboring galaxies, the presence of dark matter, and the larger-scale forces at play in the cosmos. One of the most intriguing aspects of spiral galaxies is how they are connected to the larger structure of the universe. As galaxies evolve, they interact with one another, forming groups, clusters, and superclusters. These structures are tied together by vast cosmic filaments of dark matter and gas, which stretch across billions of light years. These large-scale structures play an important role in the evolution of individual galaxies, as they can influence the movement of galaxies and their interactions with one another. Understanding how spiral galaxies fit into this cosmic web is a crucial step toward understanding the evolution of the universe itself. The future of spiral galaxies, however, is not solely dependent on their interactions with other galaxies. The expansion of the universe plays a pivotal role in shaping the long-term destiny of galaxies. As the universe continues to expand, galaxies will move farther apart, and the rate of mergers will decrease. Over vast periods of time, this could lead to a decrease in the frequency of galaxy collisions and interactions. In the distant future, we may witness the final stages of spiral galaxy evolution as they eventually fade into quiescent, elliptical forms, their spiral arms a distant memory of a bygone era. Ultimately, the study of spiral galaxies provides a window into the dynamic processes that govern the cosmos. These galaxies, with their spiral arms, bulging centers, and complex gas dynamics, offer insight into the fundamental forces that shape the universe. From their birth in the early universe to their eventual transition into elliptical galaxies, spiral galaxies represent an ongoing saga of cosmic evolution that continues to unfold before our eyes. As we continue to explore the evolution of spiral galaxies, it's essential to address one of the most intriguing aspects of their formation and transformation: the role of galaxy mergers. While spiral galaxies may seem to follow a predictable evolutionary path, they are not immune to the violent processes of galactic collisions. These mergers are a significant driver of galactic evolution, often changing the shape, structure, and fate of the galaxies involved. When two spiral galaxies collide, the gravitational forces between them can lead to the distortion of their shapes. The interaction between these galaxies can trigger waves of star formation, as gas clouds are compressed and heated by the collision. However, the true impact of a merger goes beyond just star formation. A major merger can completely transform a spiral galaxy into a different type of galaxy altogether, such as an elliptical galaxy. During such a merger, the gas and dust that make up the galaxies may be funneled into the center, forming a dense concentration of stars known as a bulge. This bulge can give the galaxy a more spheroidal shape, which is characteristic of elliptical galaxies. Moreover, the merger can result in the galaxies losing their spiral structure altogether. The violent gravitational interactions during the collision cause the galaxy's disk to lose its distinct arms, leading to a more featureless, elliptical appearance. As a result, these mergers provide insight into how spiral galaxies evolve over time, and how they might eventually transition into other forms. Even though galaxy mergers are a relatively rare occurrence in the cosmic timescale, they still play a significant role in shaping the evolution of galaxies. The Milky Way itself is on a collision course with the Andromeda Galaxy, which is expected to merge with our galaxy in about 4 billion years. When this merger occurs, the gravitational interaction between the two galaxies will likely trigger bursts of star formation and potentially alter the structure of both galaxies. The resulting galaxy may be an elliptical or irregular galaxy, depending on the specific details of the collision. Interestingly, the discovery of active galactic nuclei, AGN, has revealed another layer of complexity in the evolution of spiral galaxies. AGNs are regions at the center of some galaxies where supermassive black holes are actively accreting matter. As gas and dust fall into the black hole, they are heated to extremely high temperatures, producing powerful radiation. This process can have a profound effect on the surrounding galaxy, influencing both the star formation rate and the galaxy's overall evolution. In spiral galaxies, the presence of an AGN can be a sign that the galaxy is in an active phase of evolution. The radiation produced by the AGN can heat the surrounding gas, preventing it from collapsing into new stars. This feedback mechanism can slow down or even halt star formation in the galaxy. Over time, as the AGN winds down, the galaxy may enter a quieter phase, with reduced star formation and a shift toward the elliptical galaxy form. This feedback process also highlights the importance of the central supermassive black hole in the evolution of spiral galaxies. The growth of these black holes is closely tied to the growth and evolution of the galaxy as a whole. It's believed that the mass of the supermassive black hole is proportional to the mass of the galaxy's bulge, indicating a deep connection between the two. As the black hole grows, it influences the dynamics of the galaxy, shaping its structure and potentially altering its spiral arms. While the central black hole plays a significant role in galaxy evolution, it's not the only force at work. Dark matter continues to be a critical factor in shaping the behavior of spiral galaxies. As we mentioned earlier, dark matter forms a halo around galaxies, exerting a gravitational pull that affects the movement of stars and gas within the galaxy. This dark matter halo is thought to be responsible for the stability of spiral galaxies, preventing the stars in the outer regions from being flung out into space due to the galaxy's rotation. Dark matter is also thought to play a role in the formation and evolution of spiral arms. The gravitational influence of dark matter helps to maintain the stability of the galaxy's disk, allowing the spiral arms to persist over time. Without the presence of dark matter, the spiral arms would likely dissipate much more quickly, and the galaxy would lose its characteristic spiral shape. This connection between dark matter and the visible matter in the galaxy underscores the intricate relationship between the different components of a galaxy, and highlights the need for further research into the nature of dark matter. As we look to the future of spiral galaxies, we must also consider the role of cosmic inflation and the expansion of the universe. The universe has been expanding since the Big Bang, and this expansion continues to this day. Over time, galaxies are moving farther apart from each other, and this expansion will eventually affect the fate of spiral galaxies. As galaxies move farther apart, the rate of collisions and mergers will slow down, and the universe will enter a period of cosmic isolation. In the distant future, galaxies like the Milky Way may find themselves alone in vast regions of empty space. With no nearby galaxies to interact with, these spiral galaxies will slowly evolve into red-ended galaxies, with little new star formation and no spiral arms to define them. This process will take billions of years, but it marks the final stage in the evolution of many spiral galaxies. Yet, even in this quiet phase, spiral galaxies will continue to evolve. Over time, the stars within the galaxy will age, and the galaxy will become dominated by older, cooler stars. The gas and dust that once fueled star formation will be exhausted, and the galaxy will slowly fade into obscurity. This slow decline is the fate of many spiral galaxies, but it's not the end of their story. The study of spiral galaxies is far from over. As new technologies and observatories come online, we will continue to gather more data about these fascinating cosmic structures. The advent of advanced space telescopes, such as the James Webb Space Telescope, will allow astronomers to peer deeper into the universe than ever before. These observations may reveal new insights into the formation and evolution of spiral galaxies, helping us understand their place in the larger cosmic picture. In addition to technological advancements, future research into dark matter, supermassive black holes, and the dynamics of galaxy formation will provide a more complete understanding of the forces that shape spiral galaxies. As we learn more about the intricate processes that govern galaxy evolution, we will also gain a better understanding of the universe as a whole. The evolution of spiral galaxies is a dynamic and complex process that is influenced by many factors, including the interstellar medium, dark matter, galaxy mergers, and the presence of supermassive black holes. While spiral galaxies may eventually lose their distinctive arms and transform into elliptical galaxies, their journey through the cosmos is far from over. With each new discovery, we come closer to understanding the fundamental processes that shape galaxies and the universe itself. Spiral galaxies, with their beautiful structures and intricate dynamics, are a testament to the ever-changing nature of the cosmos, and their study will continue to inspire astronomers for generations to come. The study of spiral galaxies is not just a pursuit of understanding their structure and evolution, but also an investigation into the very nature of the universe itself. These galaxies offer a unique lens through which we can observe the larger cosmic processes, and as we continue to probe their mysteries, we may uncover answers to some of the most profound questions about space, time, and the origins of everything we know. One of the most captivating aspects of spiral galaxies is their diversity. While they all share a general structure, a central bulge, a flat disk, and prominent spiral arms, no two spiral galaxies are exactly the same. Some have tightly wound spiral arms, others have more loosely defined structures, and some even feature intricate variations in the arrangement and number of arms. This variety is a reflection of the different histories and evolutionary paths these galaxies have taken. It also raises the question, what factors determine the precise shape and structure of a spiral galaxy? The composition and distribution of stars, gas, and dust play a significant role in shaping a spiral galaxy's appearance. The star formation rate, the age and metallicity of stars, and the presence of interstellar gas all influence how the spiral arms form and evolve. Additionally, the initial conditions of the galaxy, such as its angular momentum, mass, and environment, can also have a lasting impact on its structure. These factors create a delicate balance, and any disturbance or change in these elements can lead to dramatic shifts in the galaxy's form. For example, the presence of large amounts of gas within a galaxy can enhance the formation of spiral arms, as the gas condenses into dense clouds that trigger new star formation. On the other hand, the depletion of gas over time can lead to the fading of the spiral arms and a reduction in star formation, causing the galaxy to transition toward a more elliptical or irregular form. Moreover, the interactions between galaxies, such as gravitational interactions and tidal forces, can have a profound impact on a spiral galaxy's evolution. These interactions can lead to the formation of new features like tidal tails, rings, or even the destruction of spiral arms. Some galaxies may even be stripped of their gas, resulting in the cessation of star formation and a transition to a more passive state. In the broader context of cosmic evolution, spiral galaxies represent a key stage in the life cycle of galaxies. While they may eventually evolve into elliptical or irregular galaxies, they can also act as the building blocks for even larger structures, such as galaxy clusters. These clusters, which contain many galaxies bound together by gravity, play a major role in the large-scale structure of the universe. The formation of these clusters and the interactions between galaxies within them can have far-reaching consequences, influencing the evolution of entire cosmic regions. As we peer deeper into the universe, we continue to find more examples of spiral galaxies in various stages of evolution. Some galaxies are in the midst of intense star formation, their spiral arms bright with newly born stars. Others, like the Milky Way, are more mature, with a steady pace of star formation and a relatively stable structure. Still others are in the final stages of their spiral evolution, their arms beginning to fade as the galaxy transitions into a more elliptical form. The diversity of these galaxies, and the complexity of their evolution, raises intriguing questions about the future of the universe. If spiral galaxies can evolve into elliptical galaxies, what will happen to the Milky Way in the distant future? Will it eventually lose its spiral arms and become an elliptical galaxy? Or will it merge with another galaxy, forming a completely new structure altogether? These questions are not just speculative musings. They are critical to understanding the long-term fate of the cosmos. By studying the evolution of spiral galaxies, we can learn more about the processes that govern the life cycles of galaxies and gain insight into the larger-scale dynamics of the universe. As we observe more galaxies, both near and far, we may uncover new patterns and principles that help explain the ongoing evolution of the cosmos. One area of research that has gained increasing attention in recent years is the study of the intergalactic medium, the diffuse gas that exists between galaxies. This gas, which is largely composed of hydrogen, plays an important role in the evolution of galaxies, as it provides a reservoir of material that can be accreted onto galaxies to fuel future star formation. The interaction between the intergalactic medium and galaxies can also lead to the stripping of gas from galaxies, which can influence their evolution and star formation rates. Recent observations have suggested that galaxies, including spiral galaxies, may be feeding off this intergalactic gas in a process known as cosmic gas accretion. This influx of gas can potentially reignite star formation in galaxies that had otherwise entered a quiescent phase, helping them maintain their spiral structure for longer periods. It also raises the possibility that galaxies like the Milky Way could continue to evolve for billions of years, even in the face of ongoing cosmic expansion and the gradual depletion of their gas reserves. The ongoing study of spiral galaxies, and their place within the broader context of galactic evolution, is essential for understanding the nature of the universe. As our technological capabilities continue to improve, we will be able to observe these galaxies in greater detail than ever before. The James Webb Space Telescope, which launched in 2021, will provide a wealth of new data about the formation and evolution of galaxies, allowing scientists to peer into the distant past and uncover new clues about how galaxies, including spiral ones, evolve over cosmic time. In addition to providing more detailed observations, advancements in computational modeling are helping astronomers simulate the evolution of spiral galaxies with unprecedented accuracy. These simulations allow scientists to explore how different factors, such as galaxy mergers, gas accretion, and dark matter distribution, affect the structure and evolution of galaxies. By comparing these simulations with real observations, researchers can refine their understanding of galactic evolution and make more accurate predictions about the future of galaxies like the Milky Way. As we move forward, the study of spiral galaxies will continue to be a cornerstone of astrophysics. These galaxies, with their intricate structures and dynamic evolution, provide valuable insights into the fundamental processes that shape the universe. From the birth of new stars and their spiral arms to the gradual evolution of their form, spiral galaxies offer a window into the past, present, and future of the cosmos. Ultimately, the study of these galaxies is a testament to the ever-changing nature of the universe. Like the galaxies themselves, our understanding of the cosmos is in a constant state of evolution. With each new discovery, we move closer to unraveling the mysteries of the universe, uncovering the forces and processes that have shaped galaxies for billions of years, and perhaps gaining a glimpse into what the future holds for galaxies like our own. As we continue to study the spiral galaxies of the universe, we may one day discover new phenomena, new insights, and new questions that push the boundaries of our knowledge even further. The evolution of spiral galaxies is far from a closed chapter in the story of the universe. It is an ongoing journey of discovery that will continue to captivate and inspire astronomers, physicists, and anyone with a curiosity about the cosmos. As we continue our exploration into the evolution of spiral galaxies, it's important to understand the forces that influence these galaxies throughout their lifetime. One of the most profound elements that guide a galaxy's development is the presence of dark matter. Dark matter, which accounts for approximately 85% of the total matter in the universe, exerts a powerful gravitational pull on visible matter. This gravitational influence plays a crucial role in shaping the structure of spiral galaxies. In spiral galaxies, dark matter is primarily concentrated in a vast, spherical halo that surrounds the visible components of the galaxy. This halo is not directly observable because dark matter does not emit light, but its presence can be inferred through its gravitational effects. The rotation of stars in the outer regions of spiral galaxies, for instance, does not follow the pattern one would expect based on the visible mass alone. Instead, stars in the outer regions of galaxies move faster than would be predicted by the visible matter, suggesting the presence of a substantial amount of unseen mass. This mysterious dark matter is essential for maintaining the spiral structure, as it provides the additional gravitational force necessary to keep stars in their orbits. The distribution of dark matter is not uniform. It can vary from galaxy to galaxy. Some spiral galaxies have more extended dark matter halos, while others have smaller or denser ones. These variations can significantly impact the evolution of a galaxy. For example, the amount of dark matter in a galaxy can affect how quickly or slowly a galaxy's stars move and how much gas it can retain over time. A galaxy with a larger dark matter halo may be more stable and able to maintain its spiral structure for longer periods, while a galaxy with less dark matter may be more susceptible to disruptions and changes in its shape. Another key player in the evolution of spiral galaxies is the interplay between the galaxy's disk and the surrounding environment. Galaxies do not exist in isolation. They are part of larger cosmic structures such as galaxy groups and clusters. These larger systems can have significant impacts on the evolution of spiral galaxies. In a galaxy cluster, for instance, the gravitational interactions between galaxies can lead to dramatic changes in their structure. These interactions can result in the compression of gas, the stripping of material from a galaxy's outer regions, or even the complete destruction of a galaxy's spiral arms. The Milky Way, for example, is part of a small group of galaxies known as the Local Group, and while it has not experienced any major interactions yet, the future collision with the Andromeda Galaxy could lead to significant structural changes. In some cases, interactions with neighboring galaxies can actually enhance the spiral structure of a galaxy. When two galaxies pass close to one another, their mutual gravitational pull can cause distortions in their shapes, leading to the formation of new features like tidal tails or rings. These interactions can trigger waves of star formation, creating new clusters of stars in the spiral arms and rejuvenating the galaxy's overall structure. This process can lead to what is known as galaxy transformation, where the original spiral structure of a galaxy is either enhanced or completely altered, depending on the nature of the interaction. The role of gas and dust in the evolution of spiral galaxies is also crucial. The gas that exists in a spiral galaxy's disk is primarily composed of hydrogen, the most abundant element in the universe. This gas can collapse under its own gravity, leading to the formation of new stars. The spiral arms, which are typically the sites of intense star formation, act as regions where gas and dust are compressed, triggering the birth of new stars. As these new stars form, they emit powerful radiation and stellar winds, which can blow away surrounding gas and dust, creating complex feedback loops that regulate star formation within the galaxy. Over time, the gas in a spiral galaxy can be depleted as stars form and the gas is converted into stellar mass. This depletion can result in a slowdown of star formation, leading to a gradual fading of the spiral arms. This process of gas depletion is a key factor in the transition from a spiral galaxy to an elliptical galaxy. As the gas in the galaxy becomes exhausted, the rate of new star formation decreases, and the existing stars begin to age. The spiral arms, which are composed of younger, more active stars, start to fade as older, redder stars take their place. This transition can take billions of years, and it represents the gradual aging and evolution of a galaxy. Despite this natural progression, some spiral galaxies manage to maintain their spiral structure for longer periods. For example, the Milky Way, which is about 13.8 billion years old, is still a vibrant spiral galaxy with ongoing star formation in its spiral arms. The presence of dark matter, a stable environment in the local group, and the continual accretion of gas from the intergalactic medium may all contribute to the longevity of the Milky Way's spiral structure. One of the most exciting developments in the study of spiral galaxies is the discovery of active galactic nuclei, AGN. AGN are found at the centers of many galaxies, including spiral galaxies, and are powered by supermassive black holes. These black holes can have a profound impact on the evolution of the galaxy, as their immense gravitational pull can influence the surrounding stars and gas. In some cases, the energy generated by the accretion of material onto the supermassive black hole can produce powerful jets of radiation that extend far beyond the galaxy. These jets can heat up and expel gas from the galaxy, potentially quenching star formation and altering the galaxy's evolution. AGN are a critical component of understanding how spiral galaxies evolve, as they can significantly influence the rate of star formation and the overall growth of the galaxy. Looking further into the future, the fate of spiral galaxies is closely tied to the larger-scale evolution of the universe. As the universe continues to expand, the distance between galaxies will increase, and interactions between galaxies will become less frequent. Over time, the gas in galaxies will become increasingly sparse, and star formation will slow down. This process, known as the heat death of the universe, will lead to a time when galaxies like the Milky Way no longer produce new stars, and their spiral arms will fade. Eventually, the remnants of these galaxies will drift apart, leaving behind only the faint remnants of their once vibrant structures. The ultimate fate of spiral galaxies is still a topic of active research and debate. Some scientists speculate that as galaxies age and lose their gas, they will eventually merge with other galaxies, creating massive elliptical galaxies. These mergers could reshape the galaxies into entirely new forms, with little trace of their original spiral structure remaining. Others propose that spiral galaxies could survive in a more passive state, slowly fading away as their stars age and their gas reservoirs run dry. In either case, the evolution of spiral galaxies is a slow, gradual process that occurs over billions of years, offering a glimpse into the long-term future of the universe. The evolution of spiral galaxies is a fascinating journey that involves a complex interplay of forces, including gravity, dark matter, gas, and cosmic interactions. These galaxies are not static entities but are in a constant state of flux, changing and evolving over time. As we continue to study them, we learn more about the fundamental processes that govern the universe, from the birth of stars to the interactions between galaxies and the ultimate fate of the cosmos. Spiral galaxies offer us a unique window into the universe's past, present, and future, and their study will continue to inspire awe and curiosity for generations to come. As we continue our exploration of the evolution of spiral galaxies, it's important to dive deeper into the various forces that shape them and how their unique characteristics manifest over time. One of the most intriguing aspects of spiral galaxies is the structure of their spiral arms. These arms are not static, fixed features, but dynamic, evolving regions within the galaxy. Understanding how they form and how they evolve offers significant insight into the life cycle of these galaxies. The spiral arms of a galaxy are typically regions where stars are born and where gas and dust are most concentrated. These arms are often composed of young, hot stars that emit a blue light, contrasting with the older, redder stars in the galaxy's central bulge and outer halo. The spiral structure is thought to arise from a process known as density waves, which are fluctuations in the density of stars, gas, and dust that propagate through the galaxy's disk like ripples in a pond. These density waves compress the interstellar medium, triggering new star formation as gas and dust are compressed together. This results in the bright, active regions that we observe as spiral arms. However, the exact mechanism behind the formation of spiral arms is still a topic of active research. One leading theory is the density wave theory, which proposes that the spiral arms are not composed of stars that move along fixed paths but are instead a wave-like phenomenon that causes regions of higher density to move through the galaxy's disk. As these waves move, they compress gas and dust, leading to bursts of star formation. The stars in the arms do not remain there forever. They eventually drift out of the arms as they orbit the galactic center. This motion gives the spiral arms their characteristic density wave appearance, where the arms are continually replenished with new stars. Another important feature of spiral galaxies is their central bulge. The bulge is a dense, spherical region of stars that lies at the center of many spiral galaxies. It contains some of the oldest stars in the galaxy, and its structure is thought to be a key component in understanding the galaxy's history and evolution. The formation of the bulge is thought to occur early in the life of the galaxy, with stars accumulating in the center due to gravitational forces. Over time, the bulge grows larger, and the stars within it age and evolve, eventually leading to the red, older stars that dominate this region. The size and shape of a spiral galaxy's bulge can vary widely. In some galaxies, the bulge is large and prominent, while in others, it is small or even absent. The size of the bulge is often related to the overall size and structure of the galaxy. Larger galaxies tend to have larger bulges, while smaller galaxies may have only a faint central concentration of stars. The presence of a prominent bulge in a spiral galaxy can also provide clues about the galaxy's formation history. For example, a large, tightly packed bulge may indicate that the galaxy formed quickly through the merger of smaller galaxies, while a more diffuse bulge may suggest a slower, more gradual process of star formation. The connection between the spiral arms and the central bulge is critical in understanding how spiral galaxies evolve. The presence of a large bulge can influence the movement of stars and gas within the galaxy, potentially altering the shape and dynamics of the spiral arms. In some cases, galaxies with large bulges may experience a process called bulge-bulge interaction, where the central bulges of two merging galaxies interact and reshape one another, leading to a significant change in the overall structure of the galaxy. In these cases, the spiral arms may be disrupted or even destroyed, and the galaxy may eventually become an elliptical galaxy. Another crucial aspect of spiral galaxy evolution is the role of star formation. Spiral galaxies are typically characterized by ongoing star formation in their spiral arms, which are regions of high-density gas and dust. However, star formation is not a constant process. It fluctuates over time depending on various factors, such as the availability of gas, the rate of accretion, and the presence of external influences. The rate of star formation in a spiral galaxy can be influenced by interactions with other galaxies, such as when a spiral galaxy collides with a smaller galaxy or a gas cloud. These interactions can trigger bursts of star formation, leading to the creation of new stars and the rejuvenation of the spiral arms. The rate of star formation can also be influenced by the galaxy's environment. For example, spiral galaxies located in dense galaxy clusters may experience a decrease in their star formation rates due to the stripping of gas and dust by the hot, ionized gas in the cluster. In contrast, galaxies in more isolated regions may experience higher rates of star formation due to the availability of gas from the intergalactic medium. The star formation rate in a spiral galaxy is also tied to its overall evolution. As a galaxy ages and its gas reservoir is depleted, its rate of star formation will naturally slow down, leading to a gradual fading of the spiral arms. One interesting phenomenon that has been observed in the evolution of spiral galaxies is the formation of bars. A barred spiral galaxy is a type of spiral galaxy in which the spiral arms extend from a central bar-shaped structure rather than directly from the galactic center. The formation of bars is thought to be linked to the dynamics of the galaxy's central bulge and disk. In some cases, gravitational instabilities in the disk can cause the stars and gas to accumulate in a bar-like shape, creating a distinctive feature that can alter the galaxy's overall structure. Bars are thought to play an important role in the evolution of spiral galaxies by funneling gas toward the central black hole, potentially triggering active galactic nuclei, AGN, and influencing the rate of star formation. As spiral galaxies evolve, they may eventually undergo a transformation that results in a change in their morphology. This transformation can occur through a variety of processes, such as the depletion of gas, the loss of angular momentum, or interactions with other galaxies. When a spiral galaxy runs out of gas or its star formation slows down, it may transition into an elliptical galaxy, a type of galaxy that has a more spherical or oval shape with little to no ongoing star formation. The process of transforming from a spiral galaxy to an elliptical galaxy can take billions of years, and it represents the end stage of a galaxy's life cycle. The ultimate fate of spiral galaxies is still a subject of intense scientific study. One possible outcome is that the Milky Way, along with the Andromeda Galaxy, will eventually merge, leading to the formation of a new, larger galaxy. This merger, known as a galactic collision, will likely result in the disruption of the spiral structure of both galaxies, leading to the formation of a large elliptical galaxy. This process is expected to take place in about 4 billion years, giving us plenty of time to study the dynamics of galactic collisions before they occur. Even as the Milky Way continues to evolve, its spiral arms and central bulge offer a fascinating glimpse into the life cycle of galaxies. As we look beyond our own galaxy, the study of spiral galaxies provides valuable insights into the broader processes that govern the universe. The diversity of spiral galaxies, their varying sizes, structures, and histories, helps to shape our understanding of galaxy formation and evolution. By studying the interactions between galaxies, the role of dark matter, the effects of star formation, and the influence of external forces, we continue to uncover the mysteries of the cosmos. Spiral galaxies are not just beautiful structures in the sky, they are dynamic systems that offer clues about the fundamental forces that shape our universe. Understanding how they form and evolve helps us better understand our place in the cosmos and the ultimate fate of our own galaxy. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.